will be amazing. I know it will. Yeah?
Of course.
Of course. Woo!
So in order to try to deal with technical issues from now on, you are gonna have 1 extra minute per every preparation time. So report the preparation, you have 1 extra minute to try to make the USB thing work.
So this will be concerning the opponent preparation and the moderator preparation, because for the reporter presentation, you have all already downloaded your file on the main computer. Okay, and this 1 minute that we grant you doesn't suppress the 1 minute technical timeout that you are able to use once during the whole physics fight. Yeah. We also remind everybody that for the grand finale, all the team members can appear only once on stage and not twice. Yeah. And I guess we are ready to begin. So first, I think we should introduce ourselves.
Yeah, okay. So I am Maya. I am this is my first time on the IPT. I'm the team lead of this wonderful team Croatia, and yeah, I wish you all a great fight. I'm really excited to see what you prepared today.
Thank you, Maya.
And yeah, this is Jeanne.
Yeah, I'm Jeanne. I'm the French representative. But of course, don't worry, I'm not affiliated in any way with the French team. And I know how to be an impartial chair. So we will be strict chairs, but we are very nice people. Don't worry. So don't feel offended if we cut you, but we will be very strict with the times, of course. So be aware of the clock that is going to be seen here. And now I guess we will present our dear jury members.
Yeah, we are very happy actually that this year we have 5 women and 5 men in the jury. So. Yeah, thank you all for joining us today, and we can start the introductions from the left. Wait,
So you can briefly stand up, say your name, and present yourself.
Okay, so hello everyone. My name is Jan Bichałowicz. I'm related to IPT for quite long. I was in the 5th IPT in Lausanne, Switzerland, the first time. And I'm very glad that after 10 years after the IPT organized in Warsaw, I can be a jury member for today. Thank you.
Thank you.
Hi everyone again. I hope you didn't get tired of my voice hearing me throughout all this week. I'm Anastasia, I'm IPT president. My background is in optics and telecommunications, and currently I'm an editor. Thanks everyone, and good luck to the teams.
Woo!
Hi everyone, my name is Luca Terenzi. I'm a second-year PhD student at KTH in Sweden, Stockholm. My background is in photonics, physics of medical imaging, and I've been first time in Colombia and we didn't make the finals, but I'm sure today we will see great teams with a lot of potential to show us interesting physics, so good luck.
Hi everyone, you've probably seen me. My name's Anton Lutsenko. I am from Team Finland. This year we are first year on the International Physics Tournament, and I guess Team Finland made it to the finals as a jury. I was really surprised, very pleasantly surprised. So I have my best jacket and shirt. So my background is in magnetism, in nanomagnetism. I'm doing my PhD in Aalto University in Finland. And I wish you all guys a very pleasant and constructive fight, and you all a great performance.
Hi, my name is Margaret Anderson. I am one of the team leads for USA. I'm a student at Oklahoma State University, and my background is in thin film growth. It's my first year at IPT, and I'm so excited to see this fight.
Yeah, I'm Daniel. I'm leading a research group on black holes at TU Wien, and I'm here with the Austrian team. And it's my first IPT tournament. That's probably why I'm leading the board in all three scales by judging the reporters, the opponents, and the moderators. But I just want to announce, so that you don't get offended, that I'm renormalizing my scale for the finals. Thanks.
Hi everyone, I'm Christos. I'm a PhD student in Chalmers University of Technology. I'm working mostly with uranium right now. I'm also part of the executive committee of the Execom of the IPT. I've been with this tournament for quite a lot of years now. I've been also a jury in the finals for the consecutive past 3. And I have to say that this is the peak of the IPT. This is where the anxiety, the excitement, the tension skyrockets. But also this is where we see the best, the most quality solutions, and I'm really looking forward to these fights. I've been to all the positions that have existed here. I know how you guys feel, and I know that you're gonna give us the best show today, so I'm really looking forward to it. Thank you.
Hi everyone, my name is Jen Pernille, and I'm the team leader for Denmark. I'm doing my PhD with background in quantum photonics and electron microscopy, and it's my, I think, 3rd year at the IPT, so I started in 2023. Yeah, I've never been in any of these positions, but I also made it to the finals once, which is now, so good luck.
Morning, everyone. My name is Floriana Morabito. I'm team leader of the Italian team, and for me, it's the first time here. So best luck, everyone, and have fun.
Hello, everyone. My name is Lívia. I'm team leader from Team Brazil, which is over there. This is my first time at TPT. I am a professor at the Universidade Federal de Minas Gerais, and my background is in optical microscopy and nanotechnology applied to biological samples. So wish you all a very nice fight.
Okay. Okay, thank you. And now I give words to the team. So this year we have Team France, Team Switzerland, and Team Germany. And now I give first the chance for Team France to introduce themselves.
So hello, I'm Adrian, team captain of Team France. Here we have Nino, Cleo, Cedric, Thomas, and Guillaume. And I mean, it's been a great journey for us. We've worked so much and so long, and in January, we really did not sleep that much. And we're just so happy to be here, and I mean, we hope to have a lot of fun today.
Okay, thank you. Now Team Switzerland.
Hi everyone, we're Team Switzerland. This is Hannes, this is Tamas, we have Horia, we have Rafael, and we have Luca. And I'm Elias, and I hope today that our quality of work represents our lack of sleep. So we're really looking forward to this fight. Thank you very much.
Hi, my name is Chris. I'm the team leader of Team Germany, and with me I have Malte, Pablo, Jonathan, Lena, and Konstantin. And we hope to be competing with the Swiss team on more than sleeplessness. And I do think that with both of you in the finale, there's nothing less than excellent physics to expect. So I'm very much looking forward to the next couple hours.
Christian.
Should we give it out?
I might correct you on the last thing you said. This will be more than a couple of hours.
Should we give a word for like most sleep or least sleep?
Sorry?
Should we give a word for most sleep person or least sleep person?
Anyway, so we are finally ready to start. As we traditionally do, we will begin with our captain's fights. I hope you liked the captain's fights that you've had during the whole week, because we have been working very hard on them this year. It's actually the first year that the captain's fights are ready a few days before the tournament, and we do not have to come up with the captain's fights at 2 a.m. in the morning before the physics fight. So for this first captain's fight, only the team captains will come to the stage. It will be a traditional captain's fight. So please come with a piece of paper and a pen. And then we will have 2 other captain's fights that will be more of a team effort, let's say, and that will be quite fun. I hope so. So the captain's fight will appear here. And at the end of the 2 minutes that you are going to be granted, I will read your response on your piece of paper. So please circle your answer on your piece of paper. And respect the time that is going to be given. And the clock will also be on the screen here. So, are you all ready? Yeah? Let's have a look at the first captain's fight. So you will have 2 minutes to answer the following question. And Maya, please start the clock when I give you a sign. Give you a sign, yeah? If every person in Poland jumps simultaneously, how much energy would be released? Express the result in equivalent hydrogen ionization energy. And now I will demonstrate the jump that we're talking about. So please, team captains, have a look at me. I'm talking about this kind of jump. And now the 2 minutes starts. One minute left. And please circle your answer on a piece of paper. Thirty seconds. Fifteen seconds. 10 seconds, and please circle your answer. Okay, I guess everybody's ready. So let's have a look at the answers given by the team captains before we have a look at the official answer. So team captain from France suggests that the answer is 3 times 10 to the power 27. Then we have team Switzerland, 2 times 10 to the power 32. And finally, team Germany, 1.1 times 10 to the power 20. So quite different answers here. So let's have a look at the answer. So the official answer is 10 to the power 27.68. And I must say I'm very impressed with the French team captain, who got 3 times 10 to the power 27. So he just got this one wrong. And I can attest that there are some calculation on his sheet of paper, so it's just not great luck, it's actual calculations. So I guess Team France clearly wins this captain's fight, so they get 2 points. Yep. And then, let me check again. So I guess you're first and then you agree? And then we have Switzerland, who gets 1 point. And finally, 0 point for Germany. Better luck next time, maybe? Okay, so team captains can go back to the table. Thank you very much. Okay, let's continue. This time you're going to have way more fun. So let's have a look at what's happening next. You now need to choose 2 team members who will represent your team, and be careful, no communication will be allowed with your team during the task of the captain's fight. And once you've chosen 2 team members who are going to come join me on the stage, you will have 5 minutes to perform the task, but you don't know which task it is, so you need to choose now. Choose wisely. It doesn't have to be including the team captains, of course. The 2 people on stage will be able to communicate with each other, but won't be able to communicate with the rest of the team sitting at the table. Okay, so Team France has chosen their 2 representatives. Team Switzerland seem to be also ready, and yeah, you are coming with a piece of paper, great. And we're waiting for Team Germany. Okay, please let me pass. Whoa. Thank you. Maya, I will ask your help here. When I tell you to do it, we will remove this very mysterious cloth. Okay, are you all ready? Yeah? And is the 5-minute clock also ready to be... Great. So, guess the objects. On the table in front of you, there is an exhibition of 10 mysterious objects, carefully selected by Dr., I will not pronounce this right, Krzysztof Karpies, the head of the Physics Demo Lab at the Faculty of Physics, University of Warsaw. Your task is to identify as many of these objects as you can. You're allowed to look carefully at these objects to determine what they are. You must not touch the objects. A correct answer would be either the name of this object or a reasonably accurate description of its purpose or function. Your answers will be scored against descriptions provided by the curator of this exhibition. And you will have 5 minutes to complete this task. Okay, are you ready? So I repeat, you are not allowed to touch the objects. You are allowed to go around the table. You are allowed to communicate with each other. The 2 people are allowed to communicate with each other. No communication with your teams are allowed, so please, Team Switzerland, you are very close to the table, but you won't interfere with the experiment. And I will also give you, can you give me the 3 pieces of paper on my table? Yeah, and you can distribute them. We have prepared the lists. The objects have numbers on it, and please write your answers in front of each of the 10 numbers. You only have 5 minutes, and there are 10 objects. And please be kind to each other. Don't push the others. There is plenty of space here. One question from Switzerland? Yes, the numbers will be clearly visible. Yes, we have used the judges' grades, actually. So yeah, the numbers are big. Okay, I guess we can remove the cloth, and you can start the clock as soon as it's done. And the 5 minutes begin now. Four minutes left. Yeah. Not allowed to touch these objects. I've repeated 2 times and it's written on the slide. Three minutes left. And I should be able to read your writing. I'm a teacher, so it should be okay, but still. Less than 2 minutes left.
Do you have the solutions? It's on the slide.
1 minute left. "20 seconds left. Be careful, I will collect your papers by using force if I have to. Don't know if I'm going to win this fight, but 10 seconds. In 10 seconds, you will give me your sheets, please. 4, 3, 2, 1, and Christian, stop. Yeah? He was the only one still writing, that's why. And I know his name, so. Okay, so what we suggest to do is that we have the answers on our slides, and we will check the objects one by one. We will read out loud what the teams have proposed, and then we will read you the solution. And Maya and I will be giving points or not according to the answers. If the jury members wants to intervene and have other opinions, we can also hear them. So let's have a look. There seems to be an issue with Team Germany again. I'm kidding. What's happening?
They didn't write the country.
Oh, okay, it's just a country name on the sheet. Okay, I guess it's okay. Okay, let's have a look. And there are also going to be pictures so that everybody in the audience can have a look at what the objects look like. So first, the first object, which is here, is an antique miniature induction oil, which is called a remark or coil. It dates back to the early 1900s, and it's for getting AC current from DC current source. So let's have a look at the answers given by the teams. So first, Team Germany wrote, can you read what they wrote?
No.
I will tell you what I'm reading. I'm reading doorbell.
That's a doorbell. Yeah, because
a doorbell. Okay, I guess this is 0 points. 0. Okay, then we have the French team. They propose a Quet viscosimeter. Yeah, okay, I understand why you're saying this, but yeah, this is clearly not right. And the Swiss team just wrote coil, and I guess this is the most right answer. Yeah. Okay, so you can maybe circle, on the others. Okay, let's have a look at the second object. The second object, which is this one, is an educational model of a spring showing elastic properties. So the German team wrote, function ruler to graph different functions precisely by hand. Function, tunction, punction, I don't know what it means. Anyway, it's totally wrong. So then the French team, measure string tension elasticity. This is closer to the right answer. And Switzerland is proposing store potential energy to release quickly. So they just described what a string is, actually. You could have just written string. Spring, I mean, sorry.
They didn't want to use coil twice.
They didn't want to use coil twice, yeah, okay. So what do you think, Maya, for the French and the Swiss team?
I think we should give them both points.
Yeah, I agree. So second object is correct for 2 teams. Okay, let's go on. We had this object here, number 3, which is a core memory of early computers based on ferrite rings magnetized by crossing wires with flowing current. The cross-section of wires addresses 1 bit of memory. So do you want to read the answers, Maya?
So the German team said magnetic memory array. You read it. Okay, so the French team said RAM. Yeah. So magnetic type. So it's also good. Random access memory. This one you have to read.
And the Swiss team proposed a wire grating particle detector. So I guess the French team and the German team each have the right answers, but not Switzerland this time. Yeah. Okay, let's have a look at the next one. It's a resistor decade box for adjustable values of resistances. It's this one. So, Team Germany proposed a potentiometer. Not exactly potentiometer. Okay. Okay. French team proposed a calculator. Well, this is okay. And the Swiss team proposed a unit calculator also. So this time only Germany will get 1 point. And yeah. Okay, number 5, which is here. It is a logarithmic slide ruler, an engineering tool for calculating before era of calculators and computers. So I'm wondering if the participants this year aren't too young to have guessed it right. So let's see what they've written. So we always begin by Germany, I think, yeah? So number 5? No, 6? Number 5, sorry. So you wrote an oscillator.
Yeah, so the explanation
okay.
behind this is we mixed up these 2 rows. So this was the oscillator and this was a function graph.
Yeah, but we cannot. But I mean, it's. I don't know how you guys messed it up. Okay, let's have a look at the French answer. French teams wrote slide rule for calculating exponentials and logarithmics. Correct? And finally, the Swiss team.
Scale to plot functions manually.
I don't think we can accept this answer. It's no, I don't think so. What do you think?
I mean, it's for calculating logarithms, so if you want to plot it, you can use it, but why plotting?
Yeah, no, we will not accept this. So this time, only the French team has the right answer. Let's have a look at number 6, which is here. I can't wait to hear your answers, because this one, we had a lot of conversation within Execom to know what this actually was. So this is a thyristor, a diode, here, high current, with additional lead, I don't know, LED, for controlling the amount of current flowing through it. This will be difficult to judge, I guess. So the Swiss team, German team first. German team.
It's this HV relay.
HV relay.
I don't know what's that.
I honestly don't know what that is. Okay, yeah. Not convinced about this one. French team wrote
high voltage component.
High voltage component. This is a high current component, and it's a diode, so we won't accept it. And finally, the Swiss team, number 6, a fuse. No. We will not accept this answer either, so nobody got it right. Let's have a look at the next. Number 7. 7 is here. This one. This is a cathodic ray tube for handheld oscilloscope. This is not an electron lamp.
Okay, so Team Germany actually wrote cathode ray tube, so congrats.
Congrats.
Then Team France, X-ray generator / cathode / electron beam. No, what's this?
Okay, so you guys proposed 3 different answers, and one of them is the right one, but it's a bit cheating. Like, we cannot accept it, because what do you think, Maya?
I think, like, if you don't accept the French answer, I should definitely not accept it.
I mean,
I don't know, but it's similar.
I mean, it's, yeah, okay.
If the other
no, I
teams
guess,
agree, I think we can accept.
But it's not. Yeah.
It's okay. It's okay. No? Wait, we need...
So we will ask our guest here what he thinks. Should we grant them the point or not? Yeah.
Unfortunately, in my opinion, it's not correct.
Okay. Okay, then we will not grant you the point. And finally, the Swiss team wrote...
A photo detector.
And this, I guess we can all agree that this is not the right answer. So for this one, only the German team got a point. Oh no, one more. Sorry. Yeah, of course. Number eight, this one. This is an antique amperemeter based on repelling magnet from a coil through which a current flows. Let's have a look at the German answer they wrote.
They wrote high current amperemeter.
Then the French team wrote also amperemeter. And the Swiss team wrote electric generator, which we cannot accept. Two correct answers for this one. And finally, last but not least, number 9, which was this one. 9 and 10, yes? 9 and 10.
You said
Last slide. So this one is an optical chopper based on rotation of a mirror, chopping the light beam, for instance, used in the Foucault experiment. So let's have a look at the German answer. They wrote laser reflector. I am not convinced about granting them the point. We won't give them the point. Then the French team wrote lens focal length measuring device via autocollimation. So this is wrong also. I mean, it's quite original, I must say, but no, not at all. And the Swiss team, can you read it? Oh yeah, I was looking at number 10. Okay, we will have trouble reading your number 10. A lamp. No, this is not a lamp either. No. So no points for this one. Do you agree? Yeah, okay. Let's have a look at the last but not least object, this one, which is a videotape recorder, an analog one with a characteristic inclination of a recording head path relative to the magnetic tape. Whew. Okay, let's have a look at the answers. The German answer?
Camera plus mic recorder. Okay.
We will accept this answer. French answer?
So French team is again writing 2 answers, but no, I'm kidding. So it's a tape recorder / player.
Recorder / player. And according to the description, it is only a recorder. So we'll see what we do about that. And finally, the Swiss team. Okay, now I can read it. Tape recorder. Okay, so the German and the Swiss team definitely have 1 point. And I must say, it's a bit complicated to give a point to the French team since they wrote recorder / player. So what do you think, Maya?
I think it won't change the result, so...
Currently, Germany has 5 points, Swiss has 3 points, and France has 4 points. If we grant them the last answer, France will have 5 points, just as Germany. So what we could do is grant them half a point. No, I mean, they wrote recorder / player, so if all the juries are agreeing, yeah, okay. So, congratulations, everybody. I hope you enjoyed this physics fight, yeah? So Germany is first.
So 2 points for Germany.
Yeah, 1 point for France and 0 point. Yeah.
How many minutes is the last one?
It's 5 minutes. Okay, we are slowly approaching the third and final captain's fight, which is the highlight of the week, I would say. So this will be a team effort, and for this one you will need to pay a great attention to the clock. Okay, so let's have a look at what we will ask of you. So you will have 5 minutes to perform the following task as a team. Are you all ready? Yeah? Mm-hmm. So the title is Curious Endeavors. So this fight is sponsored by the EU-funded Nuclear Energy BSc's program at the Faculty of Physics, University of Warsaw. Marie Curie, a Polish-French physicist, was amongst the discoverers of radioactivity. Each team will receive one dosimeter, and your task is to identify the most radioactive item in the vicinity. No, please, Maya, wait. Yeah. So your task is to identify the most radioactive item in the vicinity in the next 5 minutes. Please listen, everybody. Silence in the room. Yes. The outcome of the task is a photo of your dosimeter showing its reading, meaning that you don't need to bring back the object here. We just need a picture. The team with the highest reading wins. You are allowed to go anywhere, including out of this room, but you have to be back in 5 minutes. So we will launch the clock here. You can put the clock also on your phones. And if you are not back with a picture within the 5 minutes, you will be disqualified from this captain's fight. Okay, so this will be the dosimeter you are going to be using. So, Germany, Swiss, and France, please listen, because we are currently explaining to you how to use the dosimeter, so yeah. So, the detector is this part, so you should slide down this part, yeah. And then on this part, you need to switch on the sensor and make sure that the unit is count per second, CPS. Okay, and this is currently the reading of the dosimeter. When you approach something that is radioactive, let's say, you will hear click, 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 click. And the instrument, the sensor, is a bit slow to answer. So make sure that you wait a bit before making a proper measurement. It's a bit slow to detect stuff, but we tested it and it's working. Okay? Okay, we will give you one dosimeter each, and please leave your table when Maya starts the clock. You can go anywhere, but you need to be back in 5 minutes with a picture of the reading. And the captain's fight starts now. minutes left. Minutes left. Seconds left. I repeat, 30 seconds left. Seconds. So I repeat, we will need to see a picture or video of your device. We have the German team, the French team, and the Swiss team. You're also here, yes? Okay, the 5 minutes are finished. Let's have a look at the readings. Is everybody ready? The Swiss team also, you have it on your mobile here also? Okay. Okay, let's look at the French reading. French reading is 3.9. The Swiss team got 2.0. Okay. Oh my God. The German team got 6. So maybe, does any of you want to tell us where you made this measurement?
Jonathan, please go ahead.
It was a permanent light of tritium on my keychain, so it just is radioactive as fuck.
Tritium, so hydrogen. He has tritium on his keychain, like an ampule of tritium. But also we got 4 on the stone over there.
Okay, we will collect back the devices and put them here. Did you get the... Okay, great. This is yours? Yeah. We can put them back in the bag, yeah. C'est à vous, ça? C'est à vous ou pas? Is it yours? Okay. Is it yours? Yeah? Okay. We need a backup point. Oh shit, really? Qu'est-ce qui se passe?
Là, il est convaincu que le tape recorder peut aussi play.
Oui, mais les règles.
La description, ok. Ah, je suis d'accord avec la description. Attends, de toute façon, on peut départager. Je veux rester dessus.
Look at the results of the captain's fight. 4 points in total for Germany, 1 for Switzerland, and 4 points for France. So we need a backup captain's fight. This is never ending. We will never begin the first one, but we have a spare captain's fight. Don't worry. Yes, it's this one. This is a usual captain's fight, so I will again ask the 3 team captains to come to the stage, please. Again, yes. Again and again. For this one, I will only need the German and the French team captains. Yeah, nice try. Okay, the German and the French team captain. Let's have a look at our backup captain's fight. So for this one, you will have 1 minute only. Yeah, it's a quick captain's fight. I will wait for the clock to be ready. Perfect. If every person on Earth decided to reduce their carbon footprint by 1 ton of CO2 per year by planting trees, how many trees would need to be planted each year? "30 seconds left, and again, please circle your answer on a piece of paper. "15 seconds. "5 seconds. And your time is up. So the French team captain proposed 10 to the power 8.9. I don't understand how you do your calculations, but... And the German team captain, 4 times 10 to the power 10. So quite close answers. Let's have a look at the proper answer. It's 10 to the power 11.52 trees. So this means that Germany has won the captain's fights for this grand finale. Let's give them a round of applause. Then we have the French team also, congratulations. And finally, Team Switzerland. So we will ask, So now I will ask the German team in which order they want to choose their role for this final physics fight.
We would like to choose second.
Germany will choose their role second. What about the French team?
Well, we probably should just write the...
I want you to say it in the mic.
Oh, we choose first.
And the Swiss team will choose third. Okay, so let's have a look at the choice of the French team, which will determine in which order the 3 teams will report, oppose, and moderate. So the French team chooses to moderate first, then oppose, then report. Then I will ask the German team to come to the stage and choose also, and finally, the Swiss team. So Germany will report first, then moderate, then oppose, and finally Switzerland will be the first opponent. Thank you very much. Thank you. Okay, so our first reporter will be Team Germany. We don't need the opponent's challenge. You should start at the, yeah. Okay, starting now. Germany has 5 minutes to prepare.
We also have this microphone.
Shouldn't we start time when the table is done? Like, we? Because we want
Uh-huh.
Okay, no, okay, stop the clock, stop the clock.
We are not allowed to touch them, that's why we ask. Yes.
Everything.
You're shooting the rocket here? Yeah.
Okay, I can start recording now. Oh, it's already started. Wait.
It's okay. We got this preparation.
Okay.
No?
Yeah.
What's the issue?
No, it was already started. I didn't start it. Did you start it?
No, you did. It starts automatically.
Okay, I mean. No, but I didn't start it now. I came to it and it was already started 30 seconds ago. I will give them 20 seconds. Test. You?
Pablo?
Jean, we can give them this. Yeah? I think it's okay. Sorry? Just need to hold it. can ask people to go in the 2 minutes left.
I opened the presentation, so now the guy from up front is responsible, I think, but nothing happens.
Did you put it in present?
Oh, yeah. But I did not start the presentation.
this should be working. Yes. And you also have a laser. Yeah. Oh, I should see it. Yeah, it's the papers. Yes, it's not a screen.
Just hold this very, very close.
Very, very close to mouth. Okay.
Yeah, but it's okay.
Because then I. Yeah. Yes, perfect.
Oh ja, gerne. Nee, ich muss da sprechen.
We start in 10 seconds. So let's hear the first reporting presentation.
Yeah, so welcome everybody. I'm really excited to be able to present you now our problem number 60 in the PT bottle rocket. So first we'll go over the problem statement. So the task is to, out of a single PT bottle, construct a rocket which doesn't use any chemical reaction, but uses expulsion as its main principle to propel itself forward. And we should investigate the limits in terms of speed and height here. So content-wise, we will quickly introduce the PT bottle rocket, show the equations of motion we use, the simulation, and then we go over optimizing speed and height and showing the experimental results. So let's start with that. The PT bottle rocket is defined in our sense in just being a bottle which needs to expel mass, some kind of matter. Doesn't matter if it's air or water or some kind of other gas. So, which forces are actually acting on this? So from expelling the mass, we have the thrust force, and because of resistance, due to air resistance, we have the drag and also the gravity acting on it. But to further see how these forces play a role in the equations of motion of this rocket, we wrote down this formula, and it uses these 4 or 5 main equations: the adiabatic expansion of the air, the Bernoulli principle, the conservation of momentum here, the drag force, and this gravity. And here you can see I've marked the parts of the equation which are good for us, which propel us upwards in green, and the parts which we actually want to minimize in red to get the highest acceleration and therefore also the highest speed, for example. But as I'm talking about highest speed and how it connects to acceleration, we actually want to make sure to clearly state it's not the same to optimize okay, I have to press it harder. Okay, so it's actually, we want to make clear that it's not the same to optimize the speed and the height of the rocket, because there you would need different things. For example, the height is quite involved. I will come to that back later, but the speed, for the speed, we would actually don't care about what happens after the thrust phase, because after the thrust phase, you already have your highest maximum speed during the flight. And that's why we actually want to increase this as far as we can go, increase the nozzle size, increase how much mass weight, the mass weight at which the water, for example, leaves the rocket. But this doesn't necessarily lead to the highest flight, just to differentiate this. So with our equations implemented numerically in the simulation, we already were seeing, okay, the results make sense. We have like an arc. Let's try to put in the parameters for just the regular bottle, because that's what our zero ground state is, the thing we want to optimize is. And we see that, okay, we have already a height of 25 meters, for example. But then when we tried this in reality, we built a launcher and made it work. So filled up the bottle with 33% of water and compressed air, but then the reality hit us, and we noticed that's not a one-dimensional problem, but a three-dimensional one, and we have instabilities and a higher drag, so actually we don't achieve the height that we got from our simulation. So the first and most important thing would be to optimize the stability of the rocket. So for that, we investigated a lot about fin size and tip shape and how to make them as small as possible to not increase the drag too much, but also large enough that we have a center of pressure which is behind our center of gravity when it's most important, and to be able to have a stable flight with this rocket. Furthermore, we added a cone which is hollow to add stuff like a barometer and an initial measurement unit in the future. So with this, and the video now playing, you can actually see the rocket flies perfectly straight and then comes down. And then our flight result actually matches quite well our simulation here. Just to clear these things up, we measured this with a pressure sensor, which is placed, as I said, in the tip of the rocket, in here. And because of the dynamic pressure during the up and the down motion of the rocket, where the velocity is quite high, you have these. I want to go back. No, okay, whatever. We actually can only measure the pressure accurately at the tip, at the apogee of the rocket, because otherwise dynamic pressure influences our measurement and will not lead to the correct height. So when I'm showing these plots, I'm talking about the pressure at apogee. And we can confirm that it's apogee because there the acceleration unit tells us that there's actually no acceleration acting on the rocket. No drag, no acceleration no relative acceleration to gravity. So now we get back to the optimization. And there are more things than just a stable flight we need to optimize here. Actually, we divided it in 3 different categories because we did really a bunch, and because of time, I can't in detail talk about everything, but I just want to quickly go over what we did next. So we built a launcher and realized that we had to make it really precise for the rocket to launch straight and to also be able to pressurize it to a high pressure without spontaneous launching. And we actually also built a guiding rail to help with that, but then realized with a good launcher we don't need this anymore. For the thrust, we did the most optimizations. For example, we optimized the pressure by looking at the material strength and anisotropic strength distribution in the bottle, calculated where we need to enhance the bottle the most, and did so with carbon fiber. We also tried varying the nozzle size. For this, we wanted to have a really precise way of measuring, and that's why we built a thrust stand with this sensor in the bottle to measure, for example, different liquids, different nozzle sizes, different pressures, all that just on the ground, really comfortable. So, and then we also tried water additives, and I want to go in detail about these 3 things just because I found them really interesting. So, the first thing that is not completely intuitive at the start is that not the lightest rocket travels the furthest. Not the lightest rocket can go the highest. But you would assume that because, okay, it takes more energy to bring a heavy object up. But as soon as the thrust phase is over, and this is really early in our flight, it's after around 0.15 seconds. So after this, our bottle actually becomes a projectile, and it's just carried up by its conservation of by its momentum. And that's why we need to be able to somehow save this energy in the mass of the rocket, and that's why actually you don't see this peak completely to the left, but at this case 0.1 kilograms. And we can also observe that for different nozzle sizes, we have different peaks here. So when you have a lighter rocket, we want the nozzle to be small, so the thrust phase goes on longer and carries up the rocket further without it becoming ballistic. So then, next thing we wanted to quickly talk about was the water fraction. I think everybody has this week seen this before. There's an optimal water fraction because we can't just fill up the whole bottle with water, even though it intuitively would be nice to have a lot of mass to expel, but because then the air would have to compensate for the whole volume of the water leaving the rocket, we would have a huge pressure drop, as we will see later. That's why we have an optimal water volume, and as the pressure increases here, the optimum shifts to the right. So we can have more water, higher water fraction when we go to higher pressures. So, talking about this pressure drop, we actually then thought, okay, how we can optimize this to don't have this pressure drop that much. And the equation also shows that this pressure actually influences the thrust really heavily. So what we then observed from our simulation and from experience, that the pressure drop is not only because of the ideal gas law, but also because of adiabatic properties, and we see the curve under this area under this curve is really small. So wouldn't it be really beautiful to have a constant pressure here? So we looked up to different types of gases, which we then thought, okay, we just put a liquid and a gas phase in there, so the liquid phase can evaporate as the volume increases and keeps the pressure high. And we thought about butane, and then noticed, oh, propane has actually the exact right pressure for our bottle in terms of stability and also temperature, because it's really temperature dependent. And with the butane, we conducted also thrust experiments, and you can actually, just from looking at this, see that the right video is far earlier in expelling all the liquid than the left one. And this means that it's higher thrust, even though the propane we used here was at 6 bars, while the air was at 7.3. So with this faster exhaust, there also comes higher thrust. And we also don't need to carry the water that high, but still, the main advantage is that we can use now more than 33% of water in the bottle. It's actually better to fill it all the way up. And with that, we can have a really high thrust per volume of the bottle. And this then led, I'm sorry, may you stop the time because it doesn't work anymore? I can't do anything? Okay.
Okay, the clock is stopped.
Yeah,
On which slide
I'm just
were you?
waiting for the presentation, sorry, to respond. Okay, now we can go on. Okay, so here you can see actually the difference between that propane made for our rocket launches. With the same pressure, initial pressure, and the optimum water volume, we had here a height of roughly 85 meters, and on the right we have a height of 118 meters. And you can also see that our simulation overpredicts our propane model because we just assumed constant pressure. So with that, we come to our conclusion. We used increased the stability of the rocket to gain this height. Then we increased the efficiency due to the water fraction. Then we optimized the nozzle size, the shape, the weight, and the pressure in the bottle by increasing, for example, its strength of carbon fiber. And after optimizing also the CD value by making the fins smaller and stuff, we went to this height. And in the end, with the launcher and the propane, we went to this final maximum height. So I think we investigated the phenomenon. We maximized and got to a height of 180 meters.
Thank you very much. I will need
Thank
to
you very
stop you
much.
here. Thank you. Now let's hear some clarifying questions from the Swiss team. I will hand you the mic.
Okay, thank you very much. So on slide 16, for example, you had these flight equations. What exactly is gamma? Maybe I missed it. And did you measure it or take it from somewhere?
Slide 16. Yes, we took it from the paper which is cited below. Can we see it? Yeah, there it is.
Okay, do I understand correctly that in the plots on slide 15, yeah, this one, for example, you take drag into account, right?
Yeah.
How did you measure drag?
How we measure drag?
Did you measure or did you simulate or how did you?
So how I determined the drag coefficient?
Drag coefficient, exactly.
Yeah, that's a great question.
Just
can I?
If you answer, you need to answer very quickly. If it's not quick, then you can discuss it during the
Terminal
discussion.
velocity of the rocket. We measured it.
Thank you. This is efficient. Another question.
Yeah, I'm getting used to this.
On slide 19, you talk about simulations. What did you take into account in the simulations here?
So for the simulations, we took into account the equations we presented on the slide your colleague was also mentioning before. Like air, like drag, like how fast the mass is expelled. Like, okay, let's go on. Okay.
You used an accelerometer, if I understood correctly.
Exactly.
How many degrees of freedom does this measure? Is it only one direction, or do you also have orientation?
It's 6 degrees of freedom. We have
6. Okay.
3 axes for acceleration and 3 which determine directly the orientation.
For the expansion of the gas in the propane case, do you also assume that it's adiabatic?
I assumed that
yes or no?
In what? In the simulation?
You have 5 seconds.
Yes, exactly.
Did you assume that
Yes.
it was adiabatic?
Yes.
Okay, thank you very much. You have now 4 minutes to prepare. And don't forget to put your presentation on a USB stick and charge it on the main computer.
Hey, dann müssen wir an die Seite gehen. Also die Zeit. Alles gut. Alles gut, danke. Danke.
Timeout. 1 minute timeout.
3 minutes left. The Swiss team asked for the 1 minute technical timeout.
Ja, also damit meine ich.
2 minutes left. One minute left.
Nicht mehr Ende. Nicht mehr Ende.
Ja, geh einfach.
Das ist schon zu spät. Das ist jetzt egal. Er hat extra gemacht. Das ist jetzt fein. Das ist jetzt fein.
So 20 seconds left. I need someone from LOC to find our IT guy. So someone from LOC, please help. Someone is supposed to be in this window here, and he's not. And he's the one who puts the... Okay, great. I guess he's back. Yeah, Alberto and Akash were good. Thank you. You can come back.
We need a microphone.
Yeah, of course. Don't worry. We haven't started the clock. It's okay. So who will be presenting? Okay.
Yes. All right, ladies and gentlemen, everyone between. My name is Jorge Radu, and we just saw a great presentation by Pablo about problem 16, the PET bottle rocket. First, let's take a look again at the problem statement. It states that you should build your own rocket using a single PET bottle and add any modifications you like. The working principle of the rocket should be explosion, and without any combustion or chemical reactions, investigate what the limits of the height and the speed are of such rockets. And due to the thorough investigation they did, we think that this task was fulfilled. Now, first let's look at the outline of what they did. First, they explained what a PET bottle rocket is, and did a 1D flight equation that they then numerically solved. Then they showed that the optimization for speed and height are not the same. Then showed that the experimental instabilities make this a 3D problem instead of 1D problem. And then they went to use many modifications to restabilize it. Then they showed that the weight optimization is not, as you'd think, as low as possible, but that it has a minimum. And they also talked about the optimal water fraction, which again was an intuitive, so very good that they explained this. Then they had this ingenious idea where instead of using normal air, they used propane, so it goes into a liquid phase, which helps with thrust. And then compared the simulations to an experiment, showed that there's an overprediction due to constant pressure assumption. And then they showed that they reached a staggering height of 118 meters. Now, first let's take a look on the strength of the weaknesses of the theory. Yes. They did an intuitive force analysis for the acceleration. They showed this 1D flight equation, which was good for their purposes, which was based on thermodynamic and kinetic considerations. And, very important, they explained why the speed and the height is not the same to optimize. However, there were some weaknesses in this theory we found. First thing is that the stability considerations was not implemented in the simulation, or in the theory. They also did no streamlined simulations, which could have helped to get a better prediction for the drag coefficient. They used an adiabatic assumption, however, they did not justify it during the presentation, so that's something we could talk about. Also, they assumed a completely frictionless water exhaustion, even though fluid dynamics...
So basically, there is a mixture between the liquid phase and the gas phase, just to be sure that, okay, I understand well.
Yeah, exactly.
Do you have the slide where there is a comparison between the simulation and the experiment, like for the height?
Yeah.
Yeah. Here, did you do the experiment several times? Like, is there any uncertainties on your measures, like, or is it just one random measure?
Oh, yeah. The uncertainties on our measurements. So the barostatic pressure sensor is 1 millibar. 1 millibar of uncertainty there.
So the uncertainty is the one of your device.
Okay, thank you. Your time is up. The moderator now has 1 minute to prepare. 2 minutes, sorry.
I don't know, probably.
With us. Okay.
Yeah, that one is for you.
Thanks.
1 minute left.
Okay.
I'll give this one. Okay, this one to Swiss team, this is your microphone. Okay. So like each team has one. Okay. 20 seconds left. Okay, you can start when you're ready.
So hello everybody, I'll be the moderator today. I'm Cleo from Team France, so let us remind of the subject. So Team Germany had to build their own rocket using a single PET bottle and add any modifications they liked, which they explored pretty much exhaustively. So the working principle of the rocket had to be without any combustion or chemical reactions, and they had to investigate what are the limits of the height and the speed of such rockets. Okay, so let's do... Oh. Sorry, okay. So let's do a quick overview of the reporter's presentation. They explained very qualitatively how a PET bottle rocket works, which was very nice. They proposed a numerical equation for water and air thrust force. Then they optimized the stability of their experiment. They used a pressure detector to measure the height, and they did all sorts of optimizing, which was pretty fun. So, for instance, the material, the nozzle size, or the empty mass. And they then looked at what happens when you mix air and propane in order to have higher heights. Then the opponent wanted a clarification on how the drag was measured and also what was the simulation based on. They looked a little more into the adiabatic hypothesis. They asked why was propane used for more constant pressure. They asked also whether the stability was considered for the simulations. They did point out that there was a high experimental optimization. And pointed also that maybe there's a lack of confirmation between theory and experiment. So let's look a little more at the discussion. So the idea of maximizing energy was pointed out, as well as the limitations of the setup. And especially they talked about the agreement between the simulation and the experimental data, because the simulation does say that the height is going to be higher than what they actually found. So they wanted to make sure how experimentally we could have this. And also, if they had infinite money, what would they do? And so they started speaking about the shape of the bottle. However, there are still points remaining. For instance, if they had the same height always with each launch, so if the experiment is reproducible, how were the parameters measured for the simulation, and also the question of maximizing the velocity of the setup, which might be what I would like to start with both of you. So I'd invite you to come on stage, and maybe as you talked a lot about your simulations and had many optimizing
Thank you very much.
parameters, how would you explore this limit of velocity, both of you? Maybe taking, for instance, an energetical approach. So maybe the reporter, if you'd like to answer first, and then the opponent.
Okay, thank you. So for the maximum velocity, it's actually the end result, the optimal rocket, will be a far different shape, and the mechanism we would use would be also different. Like we would then widen the nozzle to be as large as the tank itself. And then the water is just a cylinder of water which gets expelled outwards. But it's not more, like if you would see it, you wouldn't call it expulsion of water. It's more like the bottle would lift up from the solid cylinder of water, and it would be so instant. You could really good model it without Bernoulli, actually, just by modeling it as a cylinder, which will be then pushed up by the pressure inside.
So you'd say it's mostly about the shape of this bottle. We'll still on the shape.
Shape, which also includes nozzle, yeah.
Yeah, of course. But maybe there are other losses somewhere. Do you think that you could optimize the speed on varying other parameters of the bottle? Which do you think is the most important?
So as you may have heard, I mentioned this different liquid instead of water. And I think one big interesting thing that could optimize both speed and height is getting a denser liquid, because then you got more mass per volume that you eject, which is what is governed by the adiabatic condition that they used. And also something with that flows easier, so the hydrodynamic resistances are lower. But I think those are things that optimize both extra speed and extra height.
Okay, that's a very good point, because you're speaking about this liquid, and in fact, you told us that propane and water was the best combination, and maybe we can go together. What are the most important parameters of this liquid combination that is making it optimal for our PET bottle rockets? So you spoke about density. Are there other parameters that made you choose propane?
So I think you meant density in terms of highest velocity, right?
Density in both cases, because if you eject more volume, more mass per volume, I think that's beneficial to height as well, right?
Okay, so I would propose a density changing liquid, which then gets faster, even though it's in the straight part of the nozzle. Just imagine the rocket shape being like this, and then there's the straight nozzle. So thank you very much. In the straight part, the liquid would be at the same velocity all the way, but what we would add, and that's when I come to different liquids, like example, carbonation to the liquid. This liquid will expand even in the straight part of the nozzle, which then leads to a higher velocity, which then leads to a higher specific impulse. And that's actually how we came to use propane. We tried beer in the rocket, and because it was just a joke, but we tried the thrust test, and beer outperformed all our other liquids. And that's how we came up with this theory. So you did speak about
expansion.
Yeah.
So
density and expansion, what other parameters maybe?
So as I already said, I think viscosity isn't a big thing. One thing that the Germans didn't talk about is the fact that when the water is ejected, the flow profile is not homogeneous, but actually there's a stick condition at the border, which means that there's definitely some shear stresses which cause resistances. And I think here lower viscosity would be beneficial, because then the losses would be smaller.
Okay, and do you have maybe an order of magnitude? Because it isn't that easy to think that we're going to have those losses on your bottles. Can you explain it in terms of the parameters they used?
Well, I don't have an exact order of magnitude right now, but I do.
Can join the discussion.
Okay, yeah, especially if you get to a turbulent flow, like we see that it's not turbulent all the time. However, especially if you have this density change,
you're right, yeah.
You get turbulences within, I think, you ejected, why I think in some cases there might be even a benefit to a smaller nozzle, which would then enforce laminar flow, which would lower this, which has a lot less resistance than turbulent flow.
May I answer on this?
Yes, of course.
So, I'm on par with this, with your opinion that the boundary layer accounts for the friction, right?
Yes.
But think about it, if you have a smaller nozzle, you actually have only boundary layer in there.
Yes.
That's why it's laminar, but that means all of your flow has to be has to suffer of this friction. That's why a larger nozzle actually has less friction, and also because the area is scaling quadratically, and the surrounding is only scaling.
We could look
linearly.
at the orders of magnitude of this boundary layer and whether they're actually relevant in our case, where we have a centimeter. But I just have a question from my teammate.
Okay.
Thank you. So it was a question brought by the open, what I found really interesting is it's an optimizing problem. So you may want to know what is the maximum height you could just reach, but theoretically, without any energy losses. So you were trying to bird this point, so maybe you could answer it.
Yes. So. Question to me about the maximum. Okay, so well, we need to get an order of magnitude for the energy lost via drag, which you'd have to, okay, so if you take the speed, the maximum speed we got is 100 meters per second. It goes via the square. It's 10,000 meters squared per second squared times density and further. I do think it's like a non-trivial, you'd get a non-trivially higher height, obviously, when you get drag. Probably, I don't know, you might have different estimations, but I'm guessing about like 150, 200 meters. That would be like a cap for the theory if you have no drag at all. Do you think that's a good estimation, or?
I think if we have no drag at all, we can just calculate it by energy
Yes.
conservation, right?
Point.
Mm-hmm.
Yeah, so yeah, then I agree. You just do the energy conservation and you would get also the result that you would need to, then actually, the fastest rocket would be the best.
Exactly.
So it would be the same optimization problem. You would be able, you would need to lose all the mass at the beginning.
One point I'd like to think about, though, for this, the maximum speed. I don't know if you looked into this, but there might be like a different volume ratio optimum for speed and maximum height, because I'm thinking like if you have to eject less mass, the speed you get. So if you have less fuel at the beginning, the speed, the mass you need to drag up with you might be lower. So there might be like a different optimum fuel ratio for the maximum speed and the maximum height.
Yes. I think your teammate had a comment. I don't know if it is to.
It does not have to do with this point, though.
Oh,
okay.
You want to tell later then?
Yes.
Do you want to answer?
On that point?
Yeah.
Yeah, I would agree that from maximizing your speed, you would have like different parameters which are the optimum, and also different water fractions there.
Yes. Okay.
Because
I guess now it's time.
So luckily we have the setup right in front of us. I see a couple of things which I would like to ask you about. So first of all, you have carbon fiber to enforce the bottle. So I'm wondering, why isn't all of the bottle covered in the carbon fiber? And then also I see the fins. Did you try to optimize the shape of the fins and the tip?
Yeah, nice. So that's a great question. So as we noticed that if you would have a sphere, the tension on the bottle in the stress of the material would be isotropic everywhere. But here we have anisotropic stresses. That's why we actually have twice the force which will rupture the bottle in the direction you see here displayed than in the other direction, than like pulling it apart. And we really wanted to minimize the weight, so we wanted to only use as minimal amount of carbon fiber as we needed to. That's why we only wrapped it this direction. So actually this is not the optimal carbon fiber wrapped rocket. We let it burst, but that's why we don't have carbon fiber everywhere.
Having this beautiful launching system, would you say that your launches were reproducible? Because we did not see statistic approach?
I don't think I have graphs on this actually, but there are three, the highest launch we did 3 times as it was.
I'm sorry, Paolo, I have to stop you here. I'm really sorry. I will be as strict for everybody, don't worry. Now we will need the reporter's conclusion, please.
So I thank you all, the moderator and the opponent, for having this great discussion and also for bringing up so many interesting points we could talk about. I really feel that we tried almost all of them and that we also would gain a lot by keeping on this conversation. And also, since this is our last report at the IPT 2025, I especially want to thank all the people for all the great discussions during the fight. And I especially want to mention Brazil, Sweden, Israel, Austria, Poland, Croatia, Italy, and Denmark for your support and kindness. Yeah.
Okay, so thank you very much. Now is the time for the questions from the jury. Since we are a bit behind the schedule, I will ask you to be quick and precise with your questions. So 1 question per person.
So on slide 19, could you go there, please? Because there is a sharp drop in the height of your simulation. Yeah, and why is that? And
So that's a great question. As I explained at the beginning, we have height measuring errors due to the dynamic pressure when the water is really fast. And you can actually see this spike as being exactly at the instant where the speed is the highest. And that's why, because you have a higher dynamic and a lower static pressure, you get a lower pressure at all overall, and the interpreted height would be higher. But I also did just put a second y-axis here, so you can see the blue thing is actually pressure, but it corresponds to the height at the apogee where the rocket is not moving.
yeah, and what about the declination?
This?
Yeah.
Yeah, this is also a really interesting question. As we didn't want to destroy a flight computer each flight we did, we constructed parachutes to guide the rockets down slowly, and also not to, because we are afraid to get hit by such speed rockets. That's why
Okay.
I see this.
Okay. Thank you, thank you. We
Thank
should
you.
proceed to other questions.
Could you please say again the maximum pressure that can support?
Can you open this slide? Yeah, maximum pressure.
Okay, sorry. So the limit of pressure that that particular
Yeah.
design can support.
So, because each fiber wrapped rocket is wrapped a bit differently, we can't say for all wrapped rockets, but the one we tested, the burst test, with the carbon fiber rocket, withstanded 22 bars of pressure, while the regular one only did 12.
12.
Yeah.
Okay, thank you.
So, also depends on temperature, by the way.
Yeah, exactly. Thank you.
I just had a very short question I wanted to make you, no, actually for you. Just wanted to allow you to answer about the reproducibility of your experiments.
Yeah, so I think my experiments are getting more reproducible because of the launcher, which is launching the rocket the exact same, or as the best we could do all the time. And as you would assume, the reproducibility would be less when you would have not a straight flight or wind or any kind of disturbances. But as the rocket came down almost next to the launcher, we know that, not next, but like 2 meters away, it actually released the rocket quite repeatedly.
Okay, and just to finalize, how many times did you do it for this one? Because I know that you had the parachute, so it didn't break. So how many times could you do it?
So,
could you
for
just
example, with this combination, we did 12 measurements, like at the last day, and the day before, we did use the different launcher.
Okay,
cool. Thanks. It was just that.
Okay.
Well, optimization problems are really always fun, especially when we have so much engineering and such an expansive parameter space. And the discussion usually becomes if you had infinite money, if you had infinite resources. But I think that in real life, sometimes you have a lot of constraints. So I would say, if you had the opposite, if you had to remove 2 things from your setup, what would you choose to remove and still have an operational bottle rocket?
That's actually such a great question, I would, because it's like imagining what you want. Like, okay, let's see. I would actually remove drag, I think, because drag is really hurting.
No, I'm sorry. I think you misunderstood.
Oh.
I would also like to remove friction, but
Yeah.
that doesn't happen.
No. Sorry,
I would like you if you were able to remove some components.
Oh.
Like 2 components.
If you had to.
You remove, you were forced to remove 2 components.
Oh, okay. The flight computer for sure, because it's only because we need to measure, and we could also measure by using video analysis from different points, for example. And I would also maybe remove the carbon fiber wrapping, because as we saw, we can go up. We only used 12 bars with the propane, and couldn't even go higher because of legal reasons. And that's why the carbon fiber was nice, but
Thank you.
Too much.
Yeah, thanks for the great presentation. So it's clear that you enjoyed this engineering aspect of the problem a lot. There was one question that, came up in the opponent's part, and then was again discussed by you in the moderating part. But I still didn't get the answer, so maybe either of you three can address this. So there should be, for a given bottle with a given amount of liquid, some maximal height just by energy conservation. So can you just estimate how far you were off from this theoretical maximum? So what's the efficiency that you achieved in terms of height maximization? You achieved 118 meters, but is this now 50% of the theoretical maximum or 90%, or how close are you? And also, I would like to get an sort of estimate what is actually the theoretical maximum in meters or whatever.
So, I mean, if a quick order of magnitude estimation tells us that it's so it's about, I don't know, it's like a few, the energy you put in. So it's, if you take, you said 12 bars, right? Yeah. So you take 12 bars, that's 12 times 10 to the 5 pascals, times the volume, how big would you say the volume of the rocket is? So the volume of the water?
The volume of air, right?
Yeah. No, the volume, the volume of air, yes.
Yeah, 660 milliliters.
660, so that times 660 milliliters would be, I don't know. I can't do it on stage, that's bad. But I think that with the drag...
Order of magnitude is sufficient.
Yeah, no. I think like probably like 30% you use through drag, because you get like really high speeds, and I think you lose a lot through drag.
Yeah, I would agree on the rough numbers, and yeah, you would have to integrate the adiabatic curve to get the energy. And yeah, for the maximum speed, I think it's...
But sorry, I didn't quite hear what is the rough number on which you agree. So
I'm agreeing on that you lose about
30%. Ah, yeah. That's okay. So okay, thanks.
It's fine. Yeah, we haven't completely calculated this.
Sure.
Okay. I have more of a material question for you. But so you heat treated your bottles either just to make them a little bit smoother or for the purpose of heat treating them. What effect does that have on your ability to hold the pressure? And can you give me a microscopic reason for that?
Oh, okay. Really interesting, I guess. First of all, what was in our mind was to alter the shape, because that's what we could predict with our simulation. Like less area, longer, then maybe you would fly higher. But as we heat treated it, we actually noticed that it got stiffer. And from experiments, you see that this stiffness also comes with brittleness. So I would assume that the pressure would be actually higher that a brittle bottle could take. But as soon as it like falls over, or if there's a slight disturbances, it would crack and then rupture really violently. And to see what's actually happening in the bottle, I would assume that the polymers would be more dense, for example, or that there's tension in the polymers. So yeah, maybe there's I know how metals get stiff, and I would assume could be something similar, but I don't know for sure about the material science.
Okay. It's hard to ask one question, but you mentioned you have on your board computer both altimeter, essentially the barometer, if I understand correctly, and the accelerometer. Yes. How do their data compare? Do you find their comparison to be, do you find their data to agree on the same numbers?
Yes, that's a really interesting question. So here we can actually see the acceleration data from the flight. And what we noticed that it maxes out. So the acceleration is sadly so high that we can't just integrate it to get our velocity, because the sensor is not designed to take such great accelerations. And it would be nice, I agree, to be able to integrate this to get the speed and then integrate it again to get the distance. But we weren't able because of the maximum ability to measure the high forces. And also because I assume there are a lot of vibration when it goes up, because there's turbulent flow behind the rocket. The accelerations may be really, you would need to have a really high time resolution on your measurement to not add up measurement errors during the integration. So we couldn't really compare the acceleration data to our pressure sensor height measuring data. But what you can see is that on start we have a really high acceleration, and then as the fast phase is over, the acceleration is almost gone, but the air drag is still there. And when you go to apogee, there's no air drag.
I see. So I got the answer. Thanks.
Okay, we don't have much time, I guess, but one very quick answer from the opponent first. The reporter spoke about optimizing the height and the speed. If you could just detail in a few words what he, not what was said in the discussion, but what he did differently to optimize the speed compared to optimizing the height.
So I think he told us that for optimizing the speed, he got a really big nozzle size. I think that's the big point that he said, because you want to eject as much water as possible, as fast as possible. And then for height, optimized regular parameters.
So, okay, so speed is the same, but just the nozzle size is different.
So for the optimization, the big point I think was the nozzle size, right?
Yeah, and weight too.
Yes.
Okay, thank you.
My question, I'll also try to be concise. So you received a value for the optimal water ratio for mixture of water and air, I think is 35% or something, right? And then when you did the water, maybe tell me the number.
It's dependent on the pressure, as I showed.
Okay, you have dependency on the pressure. And then when you do the water and propane, and do you change the value for the optimal value of the water ratio?
Yeah, so I have to credit Chris on this. He had made a really easy...
To what direction it changes?
We increase it. There's
you
a really
increase the proportion.
simple thought experience you can do to see that more water is better there.
Okay, thank you.
Okay.
Okay, so my question will be quite short, but maybe for not only for the reporter, but also opponent and reviewer, because the content of the problem state what are the limits of the speed of such a rocket. I see the whole presentation of your presentation focused on the height, of optimization of height, and how you my question for you is, where you optimized the speed? What is the highest speed you obtained in your experiment? And to the opponent, why you didn't ask for it? For the maximum speed, because you had to find maximum speed of such rocket.
Correct. Yeah, maximum height and the maximum speed.
No, but you focused mainly on height. What about speed?
Because actually I found speed not to be that interesting. It's just the bottle having a really high opening, and no, you don't need stability. Because it only goes this high, and then the maximum speed is reached, because ideally then the water is gone. And you don't need the tip, for example, or reduce air drag or something. Where air drag would might to reduce, but you don't also.
But there are different parameters you could optimize for it. Okay, so.
Yeah, so we obtained the maximum speed we got with just a naked bottle, and then we didn't try the cylinder. Well, we did try to have a wider opening. Yeah.
And as the opponent, do you agree that it should be discussed more or less in the?
Well, I think there were the reason I didn't bring it up is because I think there were more interesting things to talk about, namely like intuition for the physics and what other type of optimizations could be done. I think even though the parameters are slightly different, the nature of both these things is similar, and he did mention that he did optimize for the speed, which I think it would have been more interesting to talk about the more intricacies of the
okay, so
of the thing.
Short question to the moderator: do you agree with them or not?
I do think that speed, and even if it's also just initial speed, is very important. Also, if we think about real rockets, that's a real thing that we have to think about. And the repartition of mass on your rocket, I think, will not, and the mass of your rocket will differ whether you want to optimize speed or height.
Okay, thank you. So thank you, everyone. And now the jury has some time to decide the grades.
Ja, wirklich. Ich habe dir gesagt, das ist nicht einfach, das zu tun. Dein Job.
Sorry?
Aber das ist ein paar Sachen gemacht, ja. Nee, aber also die Jury hatte natürlich gut. Ich habe Speed nicht ganz so optimized. Ja.
Maybe you can remind everybody that no grades will be shown. That you will collect grades secretly. But you can do it.
Okay, so just a reminder for the jury, no grades will be shown, and we will collect the grades after this fight, so you cannot change them between the rounds. Can you, yes. Can you pack?
Yeah, I'm packing.
No, it's okay. Take your time. Just before the next one. Yeah, was very nice.
Yeah. Thank you very much.
It wasn't.
Have a 5-minute break, but you really say that we start at the end of the break, so it's like a 2-minute break,
So 12.
and we will set the clock here.
Okay, 5-minute break. Okay, the jury, do you have the grades? Yeah, okay, Jean will collect the grades. So please. So because of time, we're going to skip the jury feedback. I advise you strongly to talk to the jury after the fights, ask them for feedback for your presentations. I think it's nice to have feedback for the jury. And we're gonna have a break until 12:45, and we're gonna start a clock, so at 12:45 we start with the reporter preparation. Be here.
Second round is beginning now, so please everybody come back to the auditorium. Quiz team is not complete yet.
Hello, hello.
Mic's working, yeah.
Hello, hello. We are from Team Switzerland. Hallo. Ja, unter diesem Winkel. You got this, baby. You got this. Danke für die Arbeit. Also ohne das
Okay, I ask all the teams to please sit at their tables. We're going to start in 1 minute.
Vous pouvez éjecter cette pub, hein? Sorry? It's okay, it's okay. Hey, leave it. Please leave it. But it's ours, but...
On the camera, can we put it here behind this? If we put it here, is it visible? John, you can bring it even closer. No, put it here where I'm standing. Yeah. Yeah. Okay, is that okay? Because we want it visible on the camera.
Perfect.
Can you check? Yeah. Is it visible now? Slow.
Where are the markers?
Over there.
Oh, okay, perfect. Thank you.
Okay, I think we should start.
I'm fucking also with you.
Everyone, please sit down. We are starting the fight.
Was?
Alles erinnern, aber ja, okay.
Es wird schon.
Please sit down. Sit down. We are starting the fight.
I'm going to be very honest with you here. If you want to eat lunch, we need to begin the second round now. So, Luca is here, Anastasia also. We're waiting for Jan Stefan. And Anton is here.
Okay. Is the jury all here?
No, we're missing one person. Anyway, let's introduce this second round. For this second round, Team Switzerland will be reporting on oscillating ring, and Team France will be opposing, while the German team will be moderating. So as soon as we have our last jury member, we will be able to begin. Sorry? Yeah, you can write your names, please, on the whiteboard. And we also miss Livia, right? But her name was not on her. Yeah, okay.
Okay, so the reason why we are so annoying about the time is because the lunch is until 3:30, so we have to fit before.
Whoa, nice letters. Thank you. Yeah.
Okay. No. We cannot start the report of preparation before the jury is here. I wish I could put the picture of you. It was so funny. All team hype anyway.
Okay, is someone grabbing the two jury members that are missing, please?
Polish. You have a. Can you call?
Stimmt, das können wir eigentlich.
Okay, then while we're waiting, you know my favorite thing to do is to comment on the presentations. So maybe we can use this short minute to congratulate such a great beginning, such a great first round. It's really nice to see the energy that all of you brought to the stage. And of course, congratulations go to the reporter for such a great presentation, for such a great experiment, to the opponent for bringing all these physics points. But I have to specifically commend the moderator for holding the mic for the reporter. sometimes we get carried over in the antagonism of the tournament and we forget that here we all have this same love and for physics, the same passion, and the collaborativeness of this discussion was more than we expected for the first round. It was amazing, and thank you very much for bringing this energy. Let's keep it up for this second round.
Thank you, Christos, for this nice concluding remarks.
We're still missing one jury member. I hope somebody is...
Yeah, Tomasz went to get him.
Okay.
If someone has a very good joke to tell, now is a good time.
Okay, apparently Jan Stefan cannot be found.
Yeah. Yeah, now you're going to present it.
Wait, is it possible?
Yeah, it's possible. But I'm going to leave the stage for the questions.
Okay.
Yeah.
Yeah, I forgot. I never saw this in the tournament.
But it's fine.
It's good, it's good.
Hopefully.
Especially like if you did different things. If you did like, you know,
Yeah,
different
both of us
things,
are-
then
yeah.
it makes sense that everyone presents what they know best. Did you write both of your names?
They said we should only. Yeah.
Okay. He's coming. I'm gonna hand this a jury question. No, but I think we should not cut.
Jan Stefan is here. Okay, we are able to begin the second round of this grand finale of IPT 2025.
Okay, we can start. So the reporter has 5 minutes to prepare. The reporter is ready.
We are
You can-
prepared.
Yeah.
You can start whenever you're ready.
Okay, so thank you very much. We are Hannes and I'm Tomasz from Team Switzerland, and we are going to present problem number 3, oscillating rings. Now, let's start with the problem statement. So if we have 2 ferromagnetic rings, as you can see on the right-hand side, that are attached by 2 strings on the bottom and also held up by a magnet on the top in a certain place, then we will have this axis of rotation that the 2 rings are free to rotate around. We basically had to investigate their rotational motion based on some geometric and magnetic properties. And also, the question was in the problem statement about what happens if we replace the central ring by a disk, which we will investigate later. So let's now look at a video about this motion. So you can see the 2 rings in our setup held up by this very strong magnet on the top in place, and you can see that they are free to rotate around this axis of rotation. Also, let's look at the investigated parameters. Okay, we will have a bunch of geometric parameters that are maybe not that interesting, but relevant for the problem, of course. We will have the torsional coefficients of the 2 strings that will introduce a potential for the rings to rotate around. And the dynamical variables that we are looking at to solve the equations of motion are the rotational angle of the outer and the inner rings, respectively.
So let's see what this looks like in practice. So here you can see our measurement setup. It's basically a self-built structure where we attach our magnet and also the rings. And then what we do is we capture a video from below and we can track the positions of the rings as a function of time. But actually, what is the function of this magnet? Is it only just there to hold up the rings? So let's look at some basic theory. If this is the case, if the magnet is just there to hold up the rings, then we can write down the Lagrangian of the system, which is just the Lagrangian of a coupled pendulum. Here you can see the kinetic energy contribution of this Lagrangian, and then there's also this potential energy term, which is due to the coupling by the 2 strings. We can also introduce damping into the formalism. We can write down the equations of motion, and we can then solve them numerically, and we obtain these 2 eigenmodes. So one is in anti-phase, and the other one is in phase. But is this actually true? Is it just a coupled pendulum? In this video, you can pretty clearly see that there seems to be a coupling between the two rings, which is not just due to the coupling by the string, but also due to a magnetic interaction. So let's try to validate this claim. So if the only coupling would be due to the strings, this would definitely cause a harmonic potential. As you can see here, so this is a measurement that we took from the torsional coefficient of the string, and this is exactly the potential that we expect. So let's measure this potential. For this, we keep the outer ring fixed, and we let the inner ring rotate inside of this outer ring.
So how did we actually measure the potential based on the tracking? So here you can see the video of the tracking with a fixed outer ring. And yeah, okay, we plug it into this tracker program, and then we obtain measurement points for different angles with this data calibration that we did in Python. And now to determine the potential, we just have to calculate the angular acceleration numerically that we can do. We just multiply by the measured value of the moment of inertia. And then if we integrate this torque that we obtained from multiplying by the moment of inertia according to the angle phi, then we will actually get the potential. So at the end, we were able to plot these potential functions nice in Python. And now let's look at the measurement. Okay, here you can see the blue is the measurement, and we can already see that this is not a harmonic potential, right? On the edges we have this weird stuff happening, and like these unstable equilibrium points. And then if we actually look at the prediction that we had by the measurement of the torsional coefficient, that we can see on the right-hand side on this like animation, that we have to zoom in a lot to get the value for the measurement of the magnetic potential. So it is for sure not caused by the string, but it's actually a magnetic potential. So let's talk about magnetization.
So yeah, let's look at why this is, and we describe the magnetization of the two rings. So first, we look at the really simplified model of the system. So we take our two rings, we look at them from the top, and what we do is we model each of the ring as two dipoles, as you can see here. And then we calculate the potential energy of the two dipoles representing the inner ring inside of the magnetic field, which is generated by the two dipoles of the outer ring. And the line shape that we get, you can see here. And if we compare it to our measurement, we already see that qualitatively the curves kind of look the same, because at the edges we already have these unstable equilibrium points, but of course it doesn't fit really well. Let's try to improve this. So what we can do now is we can model this magnet on the top just as a dipole, which also generates a magnetic field. This magnetic field then magnetizes our two rings, and we assume that this magnetization is tangential to the two rings. This assumption is actually validated by simulations that we did in an electromagnetic modeling software. But now we want to proceed with this advanced model that we are developing. So we parameterize the two rings by two angles, theta and theta 0, and then we calculate again the potential energy, so basically the interaction between all the dipoles on the two rings, and calculate the potential energy of the system depending on this angle phi. So we have there a magnetic factor in front, and these integral expressions that you can see there are just magnetic interactions between all the dipoles, which basically depend on the geometry of the system. Here's the line shape that we get from these calculations. And as you can see, this already looks much better than this simplified model that we presented you before. And also, if we compare it to the measurements, it looks really good.
Okay, yeah, sorry.
So now we use this model and we fit this model to our measurement. So you have to note that's actually the only fitting parameter that we have in the model is this maximum potential Umax, and the shape depends on the geometric parameters of our system. We fit this magnetic potential, and as you can see, the fit really works pretty well. And now we look at if we actually have to fit this.
Yeah. So actually, we have this one fitting parameter, but we can do better. Like we simulated this system in an electromagnetic modeling software, where we basically input the geometry that you can see on the left-hand side, with which we obtain these very nice plots of the magnetic potentials, which is really nice, because if we compare this qualitatively to the advanced theory, we actually get the same kind of curves, and the only thing that we can predict with this simulation is actually the maximal potential that was fitted before, which is pretty cool. So on the left-hand side, for example, you can see that we simulated for different ferromagnetic materials with different permeabilities, and with this we were able to get this plot where we basically plot this scaling factor, this U max, in terms of the magnetic relative permeability, and we can see this nice correlation, and from this plot that we obtained by the simulation we can plug it back to the theory, and then we lose this one fitting parameter that we had.
So let's first take a step back and see what we've done so far. So first of all, first we modeled the system as a coupled pendulum, and then we measured the potential, and we saw that it's really not a coupled pendulum because the potentials don't coincide. Then we developed this advanced model where we modeled the dipole as the whole system as an array of dipoles. We measured the potential again, and we fitted the potential, and we saw that this really gives a nice prediction. And then we used simulations to get rid of the last fitting parameter that we had, which is this maximum potential that we have. Let's actually predict something with this. So here we again see our potential, and if you think about it, what we did up until now is we only looked at this potential in a small range of angles, but if you rotate the ring even further, you see that there are many potential wells. And the second effect that we have is that there is also this harmonic potential of the string, which thus rises the potential for large angles. And then we can solve our Lagrangian again, because now we have the full expression for this potential energy. Here is what we get if we solve the equations of motion. You can see there's an initial phase where the inner ring rotates really quickly inside of the outer ring, and now you can see that the system transitions to a final phase where the inner ring just oscillates around this stable equilibrium position of the outer ring. Here is a measurement with the same initial conditions, so now you also see this initial phase where the inner ring rotates really quickly, and at some point the inner ring gets captured inside of the potential well of the outer ring, and now you can see that it transitions to this final phase where there's just an oscillation of the inner ring.
Okay, now let's actually try to compare quantitatively the theory to the measurement. So we plug in the same initial conditions in the theory that we obtained from the measurements, and then you can see that qualitatively they agree really well, and quantitatively as well, besides these tipping points that we can see there. And if we look at the magnetic potential on the right-hand side, that you can also see that these actually correspond to unstable equilibrium points of the magnetic potential, which means that the theory decided to go in the other direction, basically because we have an unstable point there. But after they get captured in a given magnetic potential, that you can see that the motion is kind of harmonic, and in this final phase we can actually analytically relate the or get an expression for the frequency, like basing the theory on small oscillations that we can harmonically approximate the magnetic potential. So in this case we can analytically solve for omega in terms of the maximal potential, and it is very nice because we already told about this U max, like the scaling factor, which can be related to a lot of geometric parameters due to the advanced theory that we had, and also the magnetic relative permeability from the simulations. Now, what happens if we replace the inner ring by a disk? Basically nothing much. We will just have a scaling factor, as you can see on the left-hand side. The video also looks qualitatively the same, and the measurement that you can see there. And if we now look at the simulation for the magnetic relative permeability, it will also just cause a scaling factor. Now, to summarize, we first talked about the problem statement, and we wanted to answer all the questions that were raised there, so that we explained the phenomenon very basically at the beginning, then looked at the measurement setup and how we did different measurements. We derived an advanced theory and also modeled why this actually can, the assumptions can be made that we did there. Then we did some simulations to further validate the theory and get loose of the fitting parameter, and then we compared the motion to the theory. Thank you very much.
Thank you. So now we have. So now we have time for the clarifying questions for the opponent team.
Do we see the slide where you have the diagram for your magnet? With the field lines, I mean, just I just want to see where
sure.
how your field lines are pointing.
This is. I think this is
one of them, for example.
No, no, this is like with the simulation, you mean, right?
Yeah, that was perfect. Okay, I want to know when you calculated your potential using torque, how did you measure the torque?
Yeah, so the torque was basically measured by multiplying with the moment of inertia. Like we multiplied the angular acceleration with the moment of inertia that we measured separately, and then with this we obtained
And
the
how
torque.
did you get the acceleration? By derivation?
Like numerical derivation in the, yeah.
Sorry, is that simulated or did you measure a
No,
torque?
like this, what I explained before in the presentation, it was like how we obtained the torque from the measurements. So in the measurements, yeah, we numerically basically differentiate. So, yeah.
Okay, thank you. Okay, could you go to slide 17, please?
Yeah.
No,
yeah, sorry. No, I think the... Yeah.
All right. Here, I was just wondering, so you are making a simulation to know the field that is induced by the magnet into the rings. I'm right?
Yeah,
All right.
yeah. Like this is the advanced theory. This is not a simulation, but yeah.
All right. Okay. So could you go to the next slide then?
Yeah, sure.
All right. Okay, and just about the same thing that he pointed out, on your magnet, you have your line of the field. Could you just tell me where is the north and where is the south on the magnet? Just
Yeah,
quickly.
like on the top and the bottom. So basically, we have like a vertical polarization of the magnet.
Okay, thank you. Thank you. You can continue into the discussion. And now the opponent has 3 minutes to prepare. Okay, tactical timeout. Jean, they are taking the timeout.
2 minutes left. Seconds, 40 seconds.
Ah non, ça c'est pas le nôtre.
Technical timeout. Tu l'as pas ouvert ici?
Si. Ah, il est caché, il est là.
So, okay. So first, I want to thank the presenter for their presentation of oscillating rings, and I want to say I've seen at this point through the French and international tournaments quite a few presentations of oscillating rings. This one blows away all the other ones. It is really amazing. So, I mean, if we want to go over the subject again, I mean, we're supposed to look at the rotational movement, which was done, and relative to the influence of the parameters of the system. So the magnetic parameters, so materials, and then the geometry of the system, so the distance between the components and the size of the different rings. So, and so also we have to consider what happens with a disk. So first off, you had a great qualitative explanation of the setup. Since you had videos of setup, you had you showed how the oscillators are coupled with at first a simple dipole model and then a more complicated model, and showed the two phases of movement. Then you have a quantitative model with the Lagrangian, which was you explained all the terms, which was really nice. Then approach the damping. Then you simulate the magnetization to get an idea of what was happening magnetically. And so that allowed you to have a better description of the dipoles and therefore look at the frequency of oscillation. And then for the validity domain, you assumed that it was magnetostatic and that the interactions came from magnetic moments from dipoles along the rings. So for the experimental setup, you had a clear setup. On the camera, we could clearly see how the camera could track the angles, although it was somewhat offset from the axis of rotation, so that could maybe induce some bias in your angles. And then you did data analysis in Python. You varied the permeability, at least experimentally. You might have to go back on that by changing the material. And then you looked at replicating changing one of the rings with a disk, which was explicitly asked. So that was very nice. And so I really like the theory verification by comparing the measured potential and the actual potential. And the theoretical potential, sorry. And then I mean, the fitting was really nice and how you could verify the existence of the two phases of movement experimentally. So for the strong points, I loved how at the beginning you decomposed important parameters. You had a very clear presentation. The decomposing the terms in Lagrangian was it was great for teaching. The importance of the magnetic interaction, which for me seems to be the important part of the problem, was, I mean, that was most of your presentation, so that's amazing. you fix one of the rings to decouple the system, since we have a coupled oscillator with string effects plus magnetic effects. So decoupling is such a simple and nice solution to show what's happening. The experimental potential, that's a great graph. The qualitative model is great for getting an idea. And I mean, I have to commend the amount of simulation and calculation work you did and how well you compared the theory and the experiments. Now, for the weaker points, maybe you could look at other equilibrium positions in other positions or further out. Then we could, we'd like maybe a bit more of precision or a clearer precision of what you took from literature and what you didn't. Then maybe we should look at induction. So what happens, since we have magnets moving in a magnetic field, we could have induction happening with eddy currents. I wasn't sure for when you changed the material of the rings, did you also do that experimentally? So maybe we could go on that really quick. And we could maybe what we could work on is if we could have a more intuitive description of what the nonlinear effects do to our frequencies and our amplitudes, to have just a better feeling for it, since you have a really good mathematical explanation. So for the questions, maybe the sort of to go on the more tricky aspects is, well, what's the effect of the magnet on the string? How could that might be change its torsion coefficient? So especially since you didn't really change the mass and the moment of inertia of the rings, what happens if you load one of the rings? What sort of repercussions does that have on the whole coupling of the system? Maybe could we have like an idea of how far the magnetization go when we're going down the rings? Are they only magnetized at the top or uniformly magnetized? So are there additional positions of equilibrium? So we could also look at the sort of more intuitive look at the effect of the nonlinearity on periodicity. And maybe our first question is, what do you think of induction and eddy currents happening in the setup, since you have magnets moving in a magnetic field?
Yeah, okay. So I guess, yeah, we are starting then with the discussion. So first of all, because you mentioned this just very quickly, so about the literature, basically like all the derivations, we did that on our own, so we didn't use any literature besides like the ANSYS electromagnetic simulation software that we also cited, so yeah.
Okay, thank you. So now, if we could, maybe for me, like my first physical question.
Yeah,
so
yeah,
to
yeah,
get into
of
the
course.
physics,
Yeah, it's just
what's the? I mean, how would you discount? I mean, do you think induction and eddy currents are happening in this problem, or how would you discount it?
That's actually a very interesting question. Okay, so yeah, maybe from this slide, or I don't know, if you think about it, because of symmetry, like the dipole that I mentioned on the top is oriented vertically. So thank you very much. Can I? Oh yeah. Which means that we will have like a circular symmetry of the system. So if we rotate around this axis, there will be no flux through the rings, which means there will be no induction.
So I completely agree, and if we can make it a little clearer for the jury, if you suppose your magnet is about a dipole and you look at the flux lines, you see they're in the same plane as the ring, they're not going through the ring, so you shouldn't have induction.
Exactly. Actually, what we tried is a video, maybe you can, I think it's on the last slide, maybe, here. We tried like rotating the magnet 90 degrees, which would like induce an asymmetrical motion, and hopefully we can see it on this video. Wait. Yeah, it actually works. So you can see it will be much more chaotic behavior because we also have induction, and then the stable positions are also at different points because the magnetic forces are also pointing in other directions.
So I think, I mean, we can now discount induction. So maybe since you didn't seem to vary the masses or the moments of inertia, for example, for me the naive way to change the moment of inertia, for example, for the big ring, is I would put like two masses here. What do you think would happen?
You're
on
totally
the system?
right. We actually did this. So what we did is like we put copper rings, which like the moment of inertia was easy to calculate, which are also not magnetic, and then like glued it basically to the ring. And then if we go back to the Lagrangian maybe at the very beginning, then like the period of oscillation due to the string will be, or no, like actually both, like because you can see the moment of inertia there in the kinetic energy part. So it will like more like higher moment of inertia will lower the frequency.
So I think you have a good understanding of the moment of inertia, and maybe if I really want to go in higher, I mean, what happens at a higher order, or I mean higher order, if I were to put masses on the big ring, specifically the big ring, and then I only oscillate the small one, do you think that would have any effect on the small one?
Like in the limit of putting extremely large masses on the outer ring, then basically it will be kind of stable with very small oscillations, and the inner one will just rotate in this potential wells and not really influence the motion of the outer ring.
So what I want to get to is since this magnet here is pulling on this string here, if I put masses here, don't you think that that would change the rigidity constant of the string here and therefore change the oscillation frequency of the smaller ring?
I'm not sure what, like, okay, we have the magnet here.
You have the magnet here, you have the larger ring, you have the smaller ring, you add weights to the large ring.
Yes.
And therefore, yes, you change its moment of inertia, but you also change its mass.
Yeah.
And so do you think by putting more tension on this string that would make it more stiff?
Yeah, that's interesting. So, okay, yeah, of course, like there is a coupling between the torsional coefficient of the string and the actual lengthening, which I find very interesting. But with our measurement setup, we were not investigating these limits, and I think it would be like interesting to look into. We didn't see anything.
So maybe so we could get into the magnetization, since you really, you really went in detail with that.
Yes.
I mean, my intuition of magnets is they want to stick to each other. So I think that the magnets would want to be in the same plane. I mean, if you look for the top, they would look like this. And my understanding from your slides is they rather be at 90 degrees from each other.
That's the
Do you
stable
think
position.
that's also possible?
In this kind of setup, I don't think so. So if we look at the very simple model, and that is why we also introduced it, because it's very interesting. I don't have much time, but
okay,
we
thank
have
you. You will explain this later.
in the same direction. Okay.
The moderator has 2 minutes for questions. Microphone.
How did you characterize your ferromagnet in the experiment? Did you measure the susceptibility and remnant magnetic field?
Of the magnet itself?
Yes, the ferromagnet.
Yeah, like we had a data sheet of the magnet that we bought, so we used that.
Okay.
At some point you said that you coated or used copper in your experiment, and you also talked about eddy currents, so you introduced a conductor. How are you using the copper in there?
The copper is like basically like we only wanted to look at the effects of the moment of inertia, but it wouldn't influence any.
Thank you. These are supposed to be technical questions with quick answers.
Yes. Is there a graph which has all the experimental data, the advanced theory, and the simulation at once? Because maybe I missed it.
Yeah, maybe. I don't know. I don't know if on the same plot because it would have been like too much lines, I think, at the end.
Okay, so if I understood the plot of your magnetic dipoles correctly, the absolute value of magnetization is different between the top and bottom of the rings, right?
Exactly. Yeah.
Did you only experience like one type of motion? You talked about the initial and end phase. Are there any different phases?
Yeah, I think like depending on the initial conditions, there are some different kind of motions, but the most interesting one is maybe this transitional phase, which kind of behaves like not chaotically but unstable on the unstable equilibrium points.
Did you use also a hard ferromagnet, or I would assume that the ferromagnets you used were quite soft, so low remnant magnetic field. Did you also use a hard ferromagnet?
Yes or no?
No.
Okay, thank you. Moderator has now 2 minutes to prepare. 40 seconds left.
Can the technical assistance team please put the presentation up? We have it open.
Jacek, we need your help. We have paused the clock. Thank you. Well, problem solved.
Oh, thanks to Team Switzerland for helping us with this. Hi, my name is Christian, and I will be the moderator on problem 3, oscillating rings. So first of all, I would like to thank both of you, because the reporter has provided a very interesting presentation, and I feel like the opponent has made an interesting discussion out of it by picking up on many important points. So first, to quickly reiterate the problem statement, if we take two ferromagnetic rings of different radii and connect them by a string, we can suspend them in the air with a magnet placed above, and then the rings rotate. And so we should investigate the phenomenon with parameters magnetic permeability, moments of inertia, positions, and thickness. And also we should look into what happens if we have a disk in the middle. And I think some of these were already discussed, and some we might touch upon in the later discussion. So to summarize the report, the reporter gave an intuitive explanation of the phenomenon. They just considered all the different parameters, demonstrated the experimental setup, provided a very elaborate theory based on the coupled pendulum first, and then they will introduce magnetism based on a measured potential. Also, they did a simulation with a modeling software, which I thought is a very advanced thing to show, and described the full dynamics of the ring, compared those to the experiment with, I would at least say, some agreement was definitely there. And they also showed a formula for the frequency in the final phase and did the last part of the problem statement by comparing to a disk. As a summary of the position speech, the report was summarized, which I liked a lot. You evaluated the strong points, which I mostly agree on, and also provided some weak points, which you proceeded to kind of tackle in the discussion. And so discussed or you suggested the topics of the effect of the magnet and string torsion. But in the end, the discussion really got to eddy currents as a first point, which I feel like was mostly closed because you agreed that that was not so relevant. Then you went into this discussion about the changing mass and the moments of inertia, and also how this affects torsion. And I feel like there are still 2 points that were mentioned that are open, which is the equilibrium positions and kind of how they affect periodicity and amplitude. So maybe you can use this to get into the discussion, and then I have some further points in which direction I kind of mind to steer this, because the reporter had a slight mismatch between the theory and experiment, where at this metastable point they kind of went into different directions. And I was wondering, maybe we can explore why that happens and get some intuition on maybe some things that were not considered in the simulation that might lead to this behavior. And so there I've provided 3 points, which is about the magnetic potential, like are the conditions to define it like this even met? And also if there is dissipation by magnetic forces, that might have an effect on the problem, because I don't think it was considered yet. And of course, if you have simulation and you compare it to only one set of parameters, it is very interesting to ask, well, what if I choose a different set of parameters? Does the simulation generalize? And if we have more time, I would also talk about the sensitivity of the problem and vertically offset rings.
I propose, since I really like your questions, especially the vertically offsetting of the rings, since I think that also meshes in with the question of the additional equilibrium positions. So maybe to clarify my question for the reporter, I think your formula, the one you use for magnetic energy, is proportional to the inverse of the distance cubed. And there's a term that has a dot product between the two
dipoles,
positions of the dipoles, and one that just has the 2 dipoles.
Exactly.
And so on your simulation with 2 dipoles, your dipoles were parallel to each other, which means that this term is equal to 0. And the thing I'm saying is, if you have your 2 rings closer to each other, could you have maybe dipoles that have maybe a component of them that is aligned, and therefore have this not be equal to 0, and would that create additional equilibrium positions?
like additional equilibrium positions, I don't think that can happen just because of like the symmetry of this problem. But if we like, yeah, exactly. But if like touching up on your question also from the discussion before, like you drew this basically very nicely that the dipoles are pointing in the same direction, which means there is a repulsion between these. So by the symmetry of this problem, the dipoles want to like maximize their distance as much as possible, which is the perpendicular state of the two rings.
Okay, maybe to also make sure that both of you kind of are on the same page here. To the opponent, if you rotate this inner ring to the 90-degree position compared to the position where they're in plane, does the magnetization of the inner ring change? Do you think that?
So I do think that when the two rings are perfectly aligned, and I don't think it would go much beyond that, the larger ring is going to shield the smaller ring.
Was that also a result of your simulation?
Yes, exactly. Actually, we had a simulation because, as the moderator mentioned, the problem statement also asks for the dependence on the thickness. So here we simulated for different, like the rings for different thicknesses, and you can see, maybe go to the last slide. Where is this? Yeah, so just looking at the, yeah, now you can see it. Like looking at the forces with very small thicknesses, the force that pulls up the two rings, yeah, sorry for it's hard to see with this angle. It's like the force pulling upwards is pretty high, but if we go with larger thicknesses, we can see that this force like logarithmically drops down, which is this shielding effect that we are actually talking about. At the end, this happens because the two rings are here touching each other, which is obviously a different effect.
Okay, so do you think that in experiment this will behave the same to both of you?
So that's actually a great question. I'd want to ask if they did an experiment.
Yeah.
Did you test it experimentally or not?
Yeah. The thing is we cannot like put plots in it because of the next slide. If we compare this to a gravitational force that's pulling the ring downwards, like the inner ring cannot like just falls down because of course like gravity passes the magnetic force upwards. So with thicker rings we weren't able to do any measurements.
I'd agree that's a very fair point. If having the rings too thick makes the setup not exist anymore, we can't really consider what would happen.
Then maybe if we're already on the simulation, I would maybe like to tackle the magnetic potential. That was probably used in this, right? The magnetic potential that you measured?
Yeah, like the magnetic potential that we measured was then like compared to the advanced theory and
just a quick answer, please.
Yeah, okay, so for example this here you can see a fit with like this is the advanced theory, this is not the simulation with the electromagnetic
so when I saw the magnetic potential I was quite surprised to see that it's scalar, because usually magnetic fields, they are non-conservative, they have a vector potential, but you define a scalar potential. To the opponent, do you think that this is valid in this case? Because I do think that this is only like this should only be valid the case where there is no current density. Do you think it's okay to do that here?
General discussion has begun.
For the current density, I think we looked at the fact that induction, I mean, we both agreed that induction geometrically was not favored, so we probably don't have induction. And you talked about in your slides about magnetic hysteresis. However, I mean, at the first order, and if you have thin enough rings and you neglect shielding, since the rings are always the same distance from the magnet, they will be not. I mean, they're the outside field. They will see in general not change that much beyond the influence of the other magnet. And therefore, I don't think it will be enough to experience much hysteresis.
Okay.
However, what I see I mean, you're talking about the difference between experiment and fit. And so one part for me would be maybe there's a problem with their theory. Another thing is, since my understanding for torque is you got the acceleration of your rings off the track.
Yeah.
Right? Okay. The thing is, I mean, when you're derivating on a track, your relative incertitudes on the size of a differential size go way up. So if you have to get acceleration, you have to derivate your angle twice.
Yeah.
So do you think there'd be a way to get your energy by derivating the angle of your derivating the angle of your rings only once?
Yeah, probably it would be possible, but actually this works. And you also touched upon like this calibration that maybe there will be an offset because of the camera movement that you were able to see like a few seconds ago, that we actually like calibrated this. And we with these like
I'm
calibrations.
sorry to interrupt you, but I think you probably mostly agree on this, and we have a question from the audience.
Yes, thank you. In the beginning, you compared the energy scale of the tension of the string to the magnetic scale, and you, in the discussion, already said that induction is not really relevant. How do you think that you lose the energy that you need in order to get to a stable position?
Yeah, basically through the strings are dissipating some energy because of internal frictions. I think that's the most relevant.
Okay, then maybe.
I mean, if I can answer that question too. I don't know. In your experience, does the disc dissipate quicker than the rings?
Yeah, and you're totally right. Air
so
friction.
I'd say air friction. Yeah.
It's also important in the case of the disc, but the most important one is still, I think, the internal dissipation of the string.
Okay, maybe because it could also be relevant for that to the opponent. What do you think would happen if the reporter had used a hard ferromagnet?
What? Sorry.
A harder ferromagnet. So because the problem statement doesn't specify the remnant magnetization.
I mean, since I think it's the same problem as magnetic hysteresis, by getting the rings close to the magnet, the rings are gonna influence the magnet's field if it's a softer or a harder magnet. I mean, especially if it's a soft magnet. The thing is, since I mean the relative distances between the things don't change too much.
Exactly.
It wouldn't change much. I mean, it would affect it at the beginning, but then it'd be set.
Yeah, it's like because of the constants.
We have a mention from Team Switzerland.
If I may, I would like to draw attention to another topic that you put out, which is that theory and experiments don't exactly match at these tipping points. And I would like to point out that these tipping points are points where the are unstable equilibrium positions. And so at these points we have a behavior which isn't quite chaotic, but it depends very, very sensitively on your initial conditions and on other parameters. So predicting the precise motion there is, I think, unfeasible.
Yes.
So I saw one of the questions we didn't, if the moderator agrees, we didn't treat yet, is having a better qualitative feeling about what happens, what the nonlinearity does to the period. So maybe if we just represent, like, for high angles, the potential energy, what happens intuitively, what's the difference between our real potential with these additional wells and just a harmonic potential?
Yeah, like, okay, there is a huge difference because after a given friction, okay, we start with a given energy, it hops around, I don't know, and then let's say it lands in a given, okay, this is not a valid motion, but you get my idea, it lands in a given potential well.
Maybe a very quick final question, but to first the opponent, how would you modify the experiment to get into this regime?
What regime?
Into this regime where the kind of curvature of the potential is stronger.
I'm not sure I understand the
I'm
question.
sorry, we don't have time to answer this. Now we're going to hear the conclusion about the reporter, please.
Okay, so first of all, thank you very much for the great discussion and from both sides. First, we talked about how the induction was discarded because of geometrical constraints, basically due to rotations, and also there are no eddy currents because of the gradient of the magnetic field with rotating the inner ring is constant, so there is no change in magnetic fields. We talked about the moments of inertia, which I think is not that an interesting parameter, but of course we had to investigate that as well. We talked about the coupling between the torsional coefficient and the string, and then also the equilibrium positions, why there are only two, and why the perpendicular state is favored. We talked about the shielding effect and showed our simulations, and also the fitting of the theory, which I think became clear at the end. And where the energy is lost, I think, was a great question, thanks to the moderating team. And what if a string was much stronger? That was touched upon at the very end. So thank you very much.
Thank you. Well, we will now hear some questions from our jury members. So please keep your question short and quick. We will allow only one question per jury, and this time we are beginning on this side.
So we have pretty much in your model the dominant way of coupling is the magnetic interaction and like induced magnetism. And you, at the end of the day, regarded the string coupling, so it doesn't affect much. Did I get you right? Or it's just present in the Lagrangian, but it's not like dominant.
Exactly, like the advanced theory predictions that we showed are like the string coefficient is included in there. We just showed why it is much smaller and like
And it's
but
linear elasticity. Yes.
Sorry.
It's linear elasticity, just spring.
Yeah, exactly. Yeah,
omega.
and it was measured as well, so it's included in the theory as well.
Hi, and thanks for the nice discussion. I just have one quick question because I was writing down and maybe I missed it. But to conclude, what are the equilibrium points that you think are possible to achieve beyond your experimenting case? Like if you could improve it as well.
That's a very interesting question. I think with two rings, you can only achieve two stable equilibrium point, or like one which is perpendicular and also for each rotation. So there are a lot of them, and also it depends on the string potential, how hard it is. But maybe if you had like three rings, which is not in the problem statement, then there would be like more interesting patterns. Okay.
So I would disagree. I think depending on the orientation between the rings, you could get the dipoles to align enough to, on top of having, sorry, I'll put on the diagram. Instead of having, if you put energy here and angle here, and you have them at 90 degrees here and aligned here, I think if you graph like experimentally for two dipoles, you could get wells here that are stable but narrow.
May I ask if you think this or you saw this?
To be perfectly clear, one of the French teams reproduced it.
Okay, thank you.
I have a question about this part about ring and changing into disk. Did you try to simulate or make some prediction of a disk as a limit case of the ring with the minimum inner diameter?
Yeah.
Did you try to connect it and show it that it's almost the same or it works the same? Did you make the simulation?
Yeah, like we didn't. Maybe you have like, okay, this is one simulation, but maybe the simulation of the, where do we have it? I think it. Okay, I don't find it, but we did simulations with the disks, and what we saw is that basically if we have like the disk here, then on the because of boundary conditions, the magnetic dipoles are still aligned kind of like tangentially, and in the center we have them kind of vertically, which means that if we basically increase the thickness of the rings, then in theory, okay, we didn't do it for a lot of thicknesses, and that would be actually very interesting to do at a limit case, that at the end, like if the whole disappears, it would be the same, but we saw then the similarities in the simulation.
I would like to return a little bit to the string. Let's say in the small angle approximation, you would have something approximately linear. What do you think would happen at larger angles as you get them progressively larger?
Like for larger angles, you mean, right?
For larger and mutual rotations.
Yeah.
1, 2, 3,
I understand.
5, 10, 20.
Yeah, like how, okay, this is a very extreme case that the opponent showed us, but it's actually very good if you maybe, like, in a very extreme case, then it looks kind of like this if we go for higher angles, and then the stable point disappears, which we actually saw in the measurements as well.
I'm sorry to interrupt, but I mean the parabolic potential is, let's say, from the linear force. What do you think would happen beyond the small angle parabolic approximation?
Yeah, like, okay, this outer potential would look different, but I don't think it's that much relevant in the problem statement, because the magnetic effects were much stronger and we wanted to investigate that. But of course, if we have we are outside of this Hooke's law regime, then we will have a different potential, not harmonic potential that is added to the magnetic effects as well.
Can I comment?
Do you want to hear the opponent's answer or not?
Moderator.
Yes, but make it quick, please.
Okay, so I think, if you look at, let's start small angle. Small angle, you're going to be stiffer because you have the string plus the magnet. If you look at larger angles, though, what's going to happen is if you imagine going down the potentials like a marble going down, it's going to accelerate here, but it has to slow down when it goes back here, and then go back down. So what I think happens at high angles is the frequency would be lower than for small angles.
Okay, thank you very much, Margaret. Do you want to hear the moderator answer or not? Yeah, I'm sorry.
I will ask the reporter and moderator since you really want to talk. So we always, in your experiments, see.
Yes.
We always, in your experiments, see that the small ring is oscillating within the big ring, kind of.
Yes.
Small ring is oscillating a lot quicker. How could we reverse it? What parameters would you vary?
To like for the outer ring to rotate much faster and the inner ring not, or yeah, like it depends on the initial conditions, and the factor is that the moment of inertia of the outer ring is usually larger. An interesting experiment that we also conducted was like this copper rings, put them on the inner ring, and then like the moment of inertia of the outer ring will be smaller, and it kind of like can rotate around very quickly around the inner ring, which only oscillates a little bit. We also did measurements to this. It's actually quite interesting behavior.
So I would agree that this is a very nice way to achieve it, but I think one of the reasons why that works you did not consider in your model so far, because the copper, I think one of the reasons why it will slow down the inner oscillations is because it induces damping through eddy currents, which then of course will reduce the eigenfrequency.
Can I explain why I don't agree? Or it's not a discussion?
Do you want to eat lunch or not?
Okay, lunch.
I can answer in 2 sentences my feeling about your question. I think if you add mass to the inner ring, it would oscillate slower, so you could decorrelate more. And you could also modify the system by opening the smaller ring and attaching the string at the top and not the bottom to make the string less stiff.
Okay, let's try to keep your questions quick and efficient.
Yeah, can you go to the slide with the formula? There were 2 terms, one over rho to the 5th and 1 over rho to the 3rd. Is there some simple explanation why these 2 powers appear?
Simple explanation of the formula up there?
Yeah, well, not the whole formula, just specifically the 1 over rho cubed behavior and the 1
Oh,
over rho to the 5th.
This is the contribution from the, like we have like dipoles integrated basically on the, like one-dimensionally along the rings, and this is basically that we get from the contribution of the dipoles that are interacting between the 2 rings, and we integrate over all these different pairwise, like dipoles pairwisely.
Okay, thanks.
So far the system, if I understand correctly, has gravity pointing down. What would happen if we flip it on its side?
We also did that. The most important thing is that we can do experiments with larger thicknesses as well. The thing is that as the opponent mentioned, I think like the lengthening of the string will be also a bit different. So maybe there is an effect, but I think the effects are actually relatively small if we consider just the rotations. But like it opens a wider variety of experiments. However, it is not in the problem statement. So yeah.
Can we get a 2 second?
I think the problem is we'd start also looking at forces on top of just rotation because you don't have the rotation symmetry anymore.
Thank you.
Okay, so very quickly to each of you. What would happen if we replace the central disk with a strongly diamagnet?
Okay, should I answer first?
Yes.
Yeah. I think the equilibrium positions would flip, like it would be the parallel state. But yeah, it's kind of hard to do experiments with strong diamagnets, but that's my answer.
Okay, does the opponent has an answer?
So I think just if you just offset the magnetic potential energy they have in terms that the magnets would rather be aligned at 90 degrees.
Yes, I agree.
Okay, perfect. Final question?
Just a quick question. So you said that you controlled your initial conditions. How did you do it?
So we just like started the experiment, and then from the video analysis we were able to precisely measure the initial conditions. So we can control them some like within a certain uncertainty with like human error, but then in the tracker analysis software we can like perfectly measure out what.
And like
We started with our hands, like okay, we try to do it precisely, and then in the tracker analysis software we measure the velocities and the positions precisely.
Thank you very much. Let's give the jury members some time to decide the grades. Okay, so just a quick announcement. Since we are waiting for a bit, we're just gonna have literally a 3-minute bathroom slash water grabbing break. And we will begin the third round at this time. So please, everybody, including the jury members, our beloved jury members, be back after the break. Of course, we still need to collect your grades, yes?
presentation is not on this.
Jacek, we need you to put the presentation on the screen, please. Great, thank you. Yeah, it's going to be 12 minutes, don't worry. Okay, I will ask for some silence in the room, please, so that we can hear our very last report of the day. So you can start whenever you're ready.
Good morning to everybody. So today we are going to present the second subject of IPT 2025, bouncing honey. So when honey is dripping from a spoon, the trickle can stop flowing, oscillate up and down before flowing again. We'll have to explain this phenomenon and investigate how the oscillations depend on the relevant parameters. So we'll first present our experimental setup, then goes on to studying the period of oscillation, and lastly consider the effect of the honey properties. So what happens, what happens when you remove a spoon from a pot of honey? The flow rate which actually decreases over time, which means that you will have three different regimes. The first one with a continued jet, which is called the jetting regime. If you wait a little bit more, you'll have a transition between jetting and dripping, in which the jet is not continuous anymore, but more between the transition between continuous and oscillations. And if we wait even more, you will fall into the dripping regime, where here we actually have the oscillations that the subject talk about. You can notice on this image that the radius here at the beginning of the jet of honey is around 3 or 4 millimeters. So what we would like to do is find a way to reproduce a jet of 3 or 4 millimeters with a control flow rate to be able to study the oscillation of honey on a spoon. So how to do so? We may present now our experimental setup. So we actually choose a syringe of 3 millimeter nozzle radius, the same as the spoon, thanks to which we were able to control the flow rate. So for more detail, here is our experimental setup. So you have a syringe pump that pushes the honey into the syringe at a control flow rate. And thanks to a camera, we're able to track the tip of the jet as a function of time. The relevant parameters here are for honey, surface tension, dynamic viscosity, and density. And for the setup itself, we have the nozzle radius that we get fixed, and also the flow rate Q that we have control on. Now, we may also want to vary the honey properties. And to do so, in literature, what we often do is use honey-like liquids, but with known properties, so that we have control on them. So to vary the viscosity, we'll use silicone oil, which covers actually the total possible values of viscosity of honey, as you can see. As for the surface tension, we'll compare glycerol and silicone oil for a same viscosity. And for the density, we will not consider this parameter since it is roughly the same value here for all our liquids. So let's start our experiment with a silicone oil V5000, which means it's 5,000 times the viscosity of water. So we'll try now to study the period of the oscillations. And the first question is, are these oscillations really periodic? So you can see them for a flow rate of 0.3 millimeter per minute, say here, for example. And so what we did is that we did many measurements for just all the flow rate possible. So here, let's place in this flow rate, for example, we made many measurements of the period. And what we see is that the period between two oscillations is roughly the same over all the measurements, which means that our oscillations are actually periodic. So we have a unique period for each of our flow rates, and we can actually now study the effect of the parameters on this period. So first of this parameter that we may want to observe the effect on the oscillation period is the flow rate. And so what we did is that we plotted with the uncertainties the flow rate, the average period, as a function of the flow rate for our V5000. And what you see is that it seems hyperbolic. So we'll just check that by going into a logarithmic scale, and you see that actually you can flit with a slope of -1, and actually the period of the oscillation is inversely proportional to the flow rate. So this is experimental, and you may want to have a theoretical approach to prove also this result. So let's get deeper into what is going into this period of the oscillations. To do so, we tracked well, thanks to our camera, the tip of the lid as a function of time for just one oscillation with here this flow rate. And what you can see is that we can cut the total period into 3 different times, which are the drop formation, the times it takes now to fall, and then the time it takes to rise. And so you have these 3 different characteristic times, and you can see on the graph that these 2 ones are kind of neglectable, and so the total period is mainly given by the drop formation. So let's look at this drop formation time. So we may wonder what is the falling condition for a drop on our syringe. We have 2 forces going on here. First off, the surface tension that tends to hold the drop up, and the weight that is going to pull it downward. At equilibrium, we have these 2 forces equal, and so we can deduce the maximum volume for a drop, after which it will just fall. And so it is given by this, and we have all this value from our liquid, like the V5000, and so we can estimate this maximum volume and check, like now experimentally, that it does correspond to what we have, like we have 6 or 7 millimeter at the time our drop just fall. So now let's try to estimate this very time of the drop formation, which is what we saw, which was mainly the period. And so we have control on the flow rate. So the volume of our drop is just going to flow rate multiplied by time. And actually, the period of the drop formation is just the time it takes for our volume to reach the maximum volume after which the drop will fall. And so we can estimate the total period as the maximum volume divided by the flow rate. And here you see that theoretically, we found what we also had on our experimental relationship, like the period is inversely proportional to the flow rate. We can even estimate, if we have a given flow rate, so for example 0.3 millimeter, an order of magnitude of this period, because we can calculate also V maximum. And so we find 1 second theoretically, and comparing to our experiment, like here it's when we tracked the tip of the jet, we see that it is of good, it accords well with what we have theoretically. So now let's go into these 2 characteristic time that we didn't speak much about. So the falling time first. We tried a free fall model, and the question is, how much time would it take for a drop, if you take a free fall model, for it to just fall under a height of 0 to 14 centimeter that we had in our experiment? It should take, theoretically, 0.2 seconds. So let's see if this falling time, if this, free fall model is actually valid. What is happening here? Yeah. And so we see that if we
Jacek, there's an issue with the projection. Okay, he's not in his lounge, so Alberto or anybody, can you please go get him? Thank you. Okay.
Thank you so much.
I don't know what happened. Okay,
Right.
the clock is starting again now.
All right, so we can look at what we have on our experiment, because we had this theoretical time of free fall, and actually zooming in, you see that the free fall times is precisely of 0.2 seconds, which is validating our free fall model. So now let's look at some more interesting part, which is the rising time of the liquids, because a liquid that goes upward is not really something you can see every day. And so we have to write all the terms of the Navier-Stokes equation to see what is going on here. So we'll first have the inertia, which is the derivative of the mass times the velocity under time. And here, what we can see from the experiment is that the velocity is roughly constant during the rising time. And so this velocity term is going to go out from the derivative, but the mass here, when the mass of honey is just going up, it is accumulated honey. And so the derivative of the mass is therefore not constant. The mass is not constant over time. And so we have this expression in terms of order of magnitude for the inertia. For the surface tension, it is actually what is making our honey going up. So this is given by this formula. I may precise that here we used a book from Pierre Gilles de Gennes, and we derived derivated all the equations from there, what we had just quoted it before. As for the gravity, it is neglectable since we have a liquid going upward. And lastly, for the viscosity, you have just the dynamic viscosity times the Laplacian of the velocity, and here the Laplacian, the characteristic length for the distance is just the jet that you have here, so you have h. And so we have here all of the terms of the Navier-Stokes equation, and we can now see which one are going to be neglectable if some are neglectable. And so what we'll see is that we want to compare inertia and viscosity, and to do so, we want to make a Reynolds number. Can just stop because it doesn't.
What's going on?
I could just, I'm putting it right there, and I tried there, and it doesn't move.
Okay, did you hear Jacek? He cannot move to the next slide, apparently.
Ok, seems to have, ça va marcher. Après, il a enlevé le...
Okay, try again before we put the clock.
Okay.
Okay.
Here it works. So we want to calculate it, the comparison between the inertia and the viscosity. And so we can calculate this Reynolds number and find that we have a Reynolds of 10, which means that we can ignore viscosity compared to inertia. And so we now have just two terms in our Navier-Stokes equation, which are governing the motion of the liquid. And we can deduce from them the velocity, theoretically, and find this, if we have to go just for 14 centimeter, which is h, we find the total time it takes for the liquid to rise. So let's compare it again with the experiment, and this is actually what we roughly have for the rising time. So now let's look at the effect of the liquid properties. I mean, we saw in the theory that it should not depend on the viscosity because not any one of these depends on the viscosity. So the period should not depend on the viscosity. So let's check that experimentally. And actually, there's for two different viscosity, no main difference considering the uncertainties between the two experimental curves. As for surface tension, we should have an important dependence since the drop formation depends on the surface tension. So let's try to see what happens here. And for two different surface tension, you have a clear difference considering the uncertainties that you can even predict theoretically because it's just the ratio between the two surface tension coefficients of glycerol and V1000. Now you may wonder, what about the breakup? Because here we have a jet of honey. What is going to create the breakup? For non-viscous liquid, it is well known. It's this really plateau instability we could have here. But for viscous jet under gravity, it is much more complicated. And you see that it's fairly recent, the bibliography put here. So the breakup length actually depends here on the viscosity. That's why you can have a liquid breakup viscous jet of like 10 meters of honey when it's just 10 centimeter when you consider water. So that is kind of amazing. And for a breakup filament, viscosity also affects the growth of the rate modes, and the pitching is always at the end thanks to the viscosity. So in this subject, we're able to, but it doesn't work. In this subject, we are able to see that when honey, that is a problem, I don't know. Okay, now it works, sorry. So when honey is dripping from a spoon, we showed that there are too many parameters, that viscosity doesn't change the oscillation, that the surface tension actually changes the oscillations, that we verified this theoretically. We investigated these two different regimes, like rising and going falling. We find the theoretical velocity of rising,
Okay,
and we investigated the smooth growth and breakup that depends actually on the viscosity. Thank you.
Okay, thank you. The opponent now has the time for clarifying questions. Use the mic.
Yes, of course. If it works, which doesn't seem to be the case, I'm sorry. Yes, this way maybe. I try, but okay, that's just. I mean, maybe now it works. No, it doesn't work. Okay, I'm sorry.
Okay, maybe then let's move to another statement.
Yeah.
You said that the movement does not depend on viscosity. Is that correct?
No, I told you that the period of the oscillation does not depend on the viscosity. That's what I said. The period of the oscillation.
Okay.
But the breakup length, I told clearly that it depends on the viscosity. Yeah.
So, if am I correct that in the end you did not really use honey for your comparison, but only the other viscous fluids that
Yes.
you presented?
I
in the beginning?
motivated. I mean, I tried with honey to see what really happens with a spoon to really stick to the subject.
Okay.
And then on the literature, it is mentioned
Thank you,
that they
thank
use
you.
honey with
Thank you.
use this.
Did you observe any symmetry breaking in your setup and when you use the spoon?
Any what?
Any breaking of rotational symmetry when you use the spoon versus when you use the setup?
Of which symmetry? I don't get what you say.
Rotational
This is
symmetry.
not a technical question.
No, I meant the jet is always like invariant by rotation.
So have you tried different temperatures?
What?
Have you tried different temperatures?
Different temperatures. So yes, this is something we would have to investigate.
Okay, so to the slide where you calculated the rising time, do you consider the string to flow downwards while the drop is rising? Also,
the rising time?
Yeah, because it was written in there. Can you just show it again, then I can see it myself? I'm afraid it's not the rising time. Yeah.
Rising time. Yes. But okay, so the rising time, maybe here it will work. Yeah, it's right there.
Ah, thank you very much. So there's a mass flow.
Okay, I'm sorry, but the time is over, and you have 3 minutes to prepare. 4 minutes to prepare.
Qu'on a eu, est-ce que tu veux avoir 20 ou 30 secondes de plus au moment de la conclusion? Il y a des trucs là que tu n'as pas eu le temps de dire ou que c'était
Ouais,
trop-
peut-être. Je pourrais remettre mes
1 minute
slides.
30.
Ouais, pourquoi pas.
1 minute 30 au lieu de 2 minutes pour la conclusion?
Ouais, je veux bien.
Une solution, ce serait de sortir du PowerPoint et de pouvoir glisser sur les slides en live. Ça, tu peux...
Et est-ce qu'on pourrait pas éventuellement faire parce que là, bah là c'est sur PowerPoint parce que j'avais des animations, mais je pense que
Là, il peut glisser directement sur...
parce qu'il faut que je télécharge.
En fait, si ton équipe a le temps, oui, vous pouvez le mettre en PDF et le remettre dessus.
Yeah, like save it as PDF and just play this PDF.
C'est pour une question, je vais faire.
Je connais pas le. Quoi? Je connais pas le Danish.
T'inquiète.
Le Danish, c'est le politique.
Bah, vas-y. Je pense que je peux retrouver les...
Tu peux le télécharger Sinon, si quelqu'un. Est-ce que quelqu'un peut faire le PDF de Bounce Symphony et le télécharger? Ouais, c'est ce qu'on va faire. Ouais, faites-le pas alors.
2 minutes for your opponent's preparation. So we're going to add 30 seconds to the reporter conclusion remarks because of technical problems. So just so both teams know. We're going to add 30 seconds to the reporter concluding remarks because of the technical issues.
And the French team, of course, has agreed to this. So, yeah. Okay, let's hope we don't have any more technical issues, and we will hear the opponent's presentation in 20 seconds.
I'm the physician today, and let's first have another look again at the problem statement. The problem statement says that when honey is dripping from a spoon, the trickle can stop flowing, oscillate up and down before flowing again. The first question was to explain the phenomenon in an intuitive way, and the second question was investigate how the oscillation depend on the relevant parameters. So, as a short summary of the report, first of all, you showed that there were 3 regimes of flow: the flowing, the transition between the jetting and the dripping, and then the dripping phase. Then you showed us your experimental setup, and you used like this nozzle instead of a spoon. Maybe we can discuss about this a little bit later, whether this changes the outcome of the experiment. You did parameter variation. You used 3 different liquids that had different viscosities, different surface tensions, and different densities. Then you analyzed the periodicity of the oscillations. You had like very many formulas for this, where you splitted the oscillation into 3 different parts, and then for each you found a formula. You analyzed the effect of the flow rate on the oscillation period. Then you analyzed the drop formation time, and you modeled the falling time with free fall. These are maybe 3 points, the last 3 points that I mentioned, that we might discuss a little bit deeply in the discussion later. And yeah, your last point was that the main forces in the phenomenon were the inertia, the surface tension, the gravity, and the viscosity, which I found very nice because you really focused on the main important parameters. And in the end, you made the statement that viscosity is not an important parameter for the period, but it's important for the breakup length. So for the general evaluation, you tried an intuitive way of explaining the phenomenon with driving forces in the beginning. Maybe as a quick starter, for the discussion, we just do a short revision of this again, and that everyone understands that we're on the same page. Then you did an analysis of some parameters influencing the oscillations, the surface tension, viscosity, the mass flow, and the density. Especially for the viscosity, you said that doesn't have any impact. Suggested improvements. You did try many different liquids, but an important parameter you didn't investigate was temperature. Temperature does have an impact on viscosity, for example, but we're going to discuss about this a little bit later. yeah, you didn't analyze when the different movements happened. For example, you stated in your in the beginning of your presentation there was these three regimes like jetting, the transition, and the droplet formation and stuff. Maybe we can find an important parameter, maybe even a number that kind of tells us like if the number has this value, we have jetting or we have droplet formation or something. And yeah. At some points in the presentation, it wasn't clear whether you actually analyzed honey or you analyzed like some of your other liquids. So yeah, for the discussion points, a really big point I think will be three formulas you gave us in your presentation. First of all, for your oscillation period, for the viscosity. As you already mentioned, the viscosity doesn't have an impact for the oscillation, but in my opinion, this is really not the case. So this should be a big discussion point. Also, you mentioned the time for droplet formation. You also developed a formula for this one and stated there was like a maximal volume for this. But I don't agree with you on this page. Maybe we also have to discuss this point again. And you also developed a formula for the rising time, which we should also review again. And yeah, then, as already mentioned in my short summary, we should maybe find ways to compactify and reduce the whole system to important numbers. And in the end, maybe we should, or maybe we should even start with this one. We should start with explaining like the whole system in a short, intuitive way, so yeah, that we understand what actually happens and how the driving forces act onto the whole system.
You can start discussing.
Yes.
Yeah. So first question to you. Do you want to come up on stage?
Yes, of course.
So first question to you. I mean, we have like these really important parameters like surface tension, viscosity, density, and mass flow rate. So what is actually happening? What does cause the dripping from the spoon or from the nozzle when the honey just flows out? And maybe do you have like a mechanical comparison for this?
All right. So I mean, you mentioned you are asking why we have the dripping regime and how should we predict, for example, that if I give you a honey flow rate or something, you will be in this regime and not in the transition regime or the jetting regime. So
Right.
that's something we actually investigated. If I can.
I'm sorry, can I just, I wanted to ask whether you have like a nice intuitive explanation of why the droplets form. For example, I mean...
You mean intuitively, so maybe we could go, okay, right, let's do this, yes.
May I suggest like something? So
yes.
When the honey starts coming out of the nozzle or of the spoon, density drives the motion. But then at some point, like the thread gets thinner and thinner, and at some point surface tension wants to maximize the surface, and that's why the jets at some point break, and then the surface tension pulls it up again.
Yeah, completely. So if we look at why the drop is falling and why we have this maximum volume, is that because actually here when you have your drop that is forming, actually I told that you have the weight that is pulling it downward.
Yeah.
But here you have an interface between honey, which is favorable energetically. And so fast tension would like to keep this energetically speaking. And that's why you have this force of surface tension that is the Thomson coefficient times the radius. And so what you see is that if the drop becomes too big, then gravity will win against this.
Very nice. Just on the point where the drop becomes too big.
Yes.
So maybe you can go to the slide where you estimated the time of the drop formation with the formula of Vmax. Because I actually don't think there's a maximal volume for droplets to form. I mean, if you imagine like a very thin thread,
here.
Yeah. If you have a big thread or a thin thread, I mean, at some point both of them will form droplets, and I don't think that they have like the same volume. So maybe you might elaborate on your thesis why there's like this maximal volume where the thread breaks.
Like we experimentally see that there is the time where the liquid is accumulating, and then the jet will just fall. Maybe what you are saying is that the jet
here when the drop falls, it's not like water. It's not just the drop alone, because you have all the jets that is following actually the fall of the drop. So I don't know if the point you want to make, but here, why you don't have just many droplets and instead you have this jet is because you actually have very viscous liquids, and which is actually what is incredible by this subject. Like I told, like I saw in the literature, you can achieve 10-meter tall
that's
jet.
True. That's true. Yeah, actually.
Which
Okay, maybe we can leave this point at this point. As you just mentioned, the viscosity is a very important parameter in this. So your last statement was that viscosity doesn't influence the droplet formation. Okay, assume we leave like every
I didn't tell
the oscillation time. Sorry.
Yeah,
right?
because I mean, it depends of what you are telling about droplets, because actually here, if you won't have a viscous liquid, this would just get fragmented into droplets. And so what I say is that the time at which this drop will fall does not depend on the viscosity. But I do say that the breaking between this, the jet, and the drop does depend on the viscosity and was studied in the literature.
Okay. But I mean, I thought you made the statement in the end that the oscillation time doesn't depend on viscosity, right?
Yeah, the oscillation time, right? Because
okay, then just can we make like this thought experiment?
Yes.
Assume we have one material that
Yes.
just has a dropping, like honey, and then we rise the temperature. Rising the temperature makes the viscosity way less, and at some point you will see, maybe you can see videos of this. If honey gets very hot, it just behaves basically like water. It just there's just no droplet formation again. There's just jetting.
Yes.
So maybe you can just elaborate on this, how your model works in this situation.
Yes. Okay. This is an interesting point. One first thing that we might say is that when you are raising the temperature, you have to be cautious that you also are raising the surface tension.
Your time is up. And now the moderator has time to ask questions.
Yes.
Moderating team, where is your microphone?
Yes.
Can you go back to the very first slide you showed us about the setup?
This one.
Yes.
Yes.
So to get out the liquid at a constant rate, you press from above with this.
We press from above with the syringe pump.
Okay.
Okay. Can you go back to slide 13, please? Okay, so here on this video we saw that the honey was moving sideways. What is causing that?
Yeah, it is very sensitive to fluctuations. So when conducting a measurement, you have to make sure that it is not, deflected too much.
If I understand correctly, you always did experiments with constant mass flow rate. Is that correct?
No, we varied the mass flow rate.
Okay.
You can see here we did the measurements for
No,
all these different
throughout one run of the experiment, mass flow rate was held constant.
What?
Throughout one run of the experiment, mass flow rate was held constant.
Yes.
Okay.
Actually.
Thank you.
So you showed us your model for the rise and fall time.
Yes.
Did you verify this experimentally as well?
Yes, actually. It is right here. We compared the falling time to the experimental one.
How much data did you get?
How much data?
So here I see this for one, but did you...
Yeah. We would track many oscillations, and then you know that the period is always the same. You can deduce statistical uncertainty from the many measurements we did here. Like we tracked the period a lot of time, and it was always the same, and we had an uncertainty thanks to that. So we made the measurement many times.
Thank you.
Thank you.
Okay. Thank you. Now you have 2 minutes to prepare.
Okay, nur die Pfeiltasten, oder?
Yes, it's mine. Ah, yes, the key. I don't know. No, I think it's the German one.
No, that's not a flash drive, that's a dongle. That's for the pointer, I think.
Yeah, it's for the pointer. You should put it. Sorry, trying.
Ja, kannst du mich habe auch schon. Danke. Deine Punkte? Nein, ich habe nicht alles gesehen. Ah ja, ich habe alles angeschaut. Die Viscosity ist eine gute Punktbestrafung. Ja, ja, mega. Also werde ich auch machen. Okay. Okay, danke. Oh, gibt's irgendwie nicht? Nein, gibt's nicht. Egal. Okay. Ich habe nur da den Bildschirm. Willst du einen Laserpointer haben? Nein, ich würde gerne vor mir das Zeug haben, dass ich nicht da unten lesen muss, aber egal. Ja, kannst du einfach auf der Slide mitklicken, wenn ich da klicke? Danke. Okay, I think we're ready. Hi, I'm Elias, and I will be moderating the discussion on this problem number 2, the bouncing honey. So before we get into the details, I want to recap the problem statement, which asks us, when honey is dripping from a spoon, the trickle can stop flowing, oscillate up and down before flowing again. We are asked to explain this phenomenon and investigate how the oscillations depend on the relevant parameters. Now, in my opinion, there is a lot of ambiguity in this problem statement, which we should clarify before we move on with this discussion. So the way you can understand this is twofold. Either you understand the problem as when the honey is flowing from a spoon, the trickle can stop flowing and start dripping, or you understand it as when honey is dripping from a spoon, then you can have a thread extending, releasing a drop, contracting, and then extending again. So what we're talking about here is either different flow regimes or a single bounce of the honey. And as I've seen in the presentation by the reporter, what they focused on was mostly the single bounce. Okay, so let's get to the outline of the report. You showed us experimental videos to visualize the chatting transition and the dripping regime. You used a cool syringe setup to control the flow rate accurately, and you introduced the relevant parameters for honey, which you mentioned were surface tension, dynamic viscosity, and the density. You used other liquids instead of honey to vary these experimentally. You showed us in the end that you would, in the drop formation, look at 3 regimes. You looked at the drop formation, you looked at the drop fall time, and you looked at the retracting time. For each of those, you showed some rough calculations and that they would align with your experiments. All right, I think the opponent then captured what you did in your report quite well and gave a good understanding of what you showed. She told you that you had a good intuitive way of explaining what happens, but you should give more analysis on the parameters which are influencing this. And it suggested improvements such as temperature measurements and different motions and different phases to be analyzed. The discussion points that were discussed between you two were an intuitive explanation of the process. I think this was mostly closed in the discussion. You had an estimation of the drop formation time. The opponent criticized that there should not really be a maximal volume, but then the reporter argued that because of the high viscosity, there is only one droplet. Now, to the open point which was left in the discussion, this was if viscosity is relevant. And I think this is a point where we should start up. The reporter says that the oscillation time between the drop formation is independent on viscosity, and I think the opponent disagrees. So if I could invite you both on stage, I would like to start the discussion at this point. Okay. So opponent, what is your opinion on the reporter?
Thank you very much for this discussion point. It's a very important one in my opinion. So if the way I think about this, like the viscosity, if we compare it to a mechanical model, for example, like a mechanical oscillation, viscosity should kind of relate to damping. So in my opinion, the oscillation time really depends on viscosity. Also because of the fact that viscosity really changed like the flow regimes. And with very low viscosity, for example with water, we don't observe like the dripping motion at all. So I really think viscosity is an important parameter even within the oscillations.
Okay, so do you have any points about this?
Yes, I don't know if it's possible to put my presentation because I had something on that. But what I could say is that actually if you have too high viscosity, there is an ignoble price on that, which is called this is an experiment in which you see that the drop is not falling at all until like 10 years. And here it is because actually viscosity is equal to damping, and I totally agree with you, but it is for far a more important value of viscosity than the one we have here in honey and that we showed in the beginning of our slides. Then maybe another point that about temperature.
I would like to keep on viscosity for a second. I think the confusion might also stem from the fact that if you do, in real life, if you dip a spoon into honey and watch it drop, then it does seem like there is a dependence on viscosity. But in a real life experiment, when you dip your spoon into honey, you will not have a constant mass flow rate. So maybe do you have thoughts on how the constant mass flow rate or non-constant mass flow rates impacts this parameter?
Okay, so in our setup, we do control the mass flow rate, and that is why we used it, because it is changing. But about the temperature and the viscosity, because the temperature, as the opponent pointed out, actually change the viscosity. It is also changing surface tension. So you might see just like little droplets and not a jet anymore. And so I think it is not really accurate to just speak about the viscosity without taking into consideration the effect of surface tension that is changing.
Can I just, okay, yeah, I think you raised a very important point here, because the mass flow rate is also an important parameter here. Maybe just a side effect, like your experiment was very nice, but like the honey dripping out of a nozzle is very different from dripping from a spoon. But yeah, now my point. When you have like the droplet formation, you said that the rising motion, gravity is doesn't, or we can neglect gravity, and here comes in the mass flow. While the drop is rising, there's also a mass flow rate coming from the top. So, and since gravity really can't be neglected here, I think mass flow rate should also play an important parameter also in the oscillation. So,
all right, yeah, you're completely right. So, to answer, I think that gravity is not of importance in the rising time, just because you lost the main part of your mass when the top, like here, the tip, just get breaked, and so you had separation between the jet and this, which constitutes most of the mass. And so you know that you have, when it falls, you have equilibrium between surface tension and weight. And so if you drop this, it means that the equilibrium is no more existing, and you have like a lot of surface tension with poor gravity. So that's why we're neglecting it.
Okay, I think an important point that was raised here was the mass flow rate that you held constant. Now I would like to hear the opponent's intuition. If the dropping of the honey actually only happens if I have mass accumulating at the bottom, does this always happen? Is the mass flow rate important? Is it not?
Sure, the mass flow rate is important, like in a sense of, if you imagine like a very big flow of honey, then the drop will probably, there's a lot of mass going down, and then the thread might break way earlier than if you just have a very thin flow of honey. So mass flow rate really also influences our system here.
Yeah, and that's why I said the different regime, and you see actually that depending on the flow rate, you'll have different behavior, and it's what you see on your spoon.
Okay, I think we have a question from the team.
I think a main confusion that's raised here is if you have a spoon in honey, you can have a difference in the flow rate. And so if you see the flow cutting on it, I mean, the flow stop and start, you don't know if it's because the flow rate is stopping and starting, or if it's into the parameters of the honey doing that. And so our approach is to think, well, what's the minimum condition to have oscillations? Does it still happen at a constant flow rate? Because you might as well say, well, if I vary the mass flow rate, I mean, if I take a tap and I turn it on and off,
sure,
the oscillate, you have a...
Yeah.
Yeah.
I really like the idea that you try to just vary other parameters and made the mass flow rate constant by using a nozzle. I just wanted to raise a point that it is still different when dropping from a spoon. But I like your idea for the experiment as well.
So there are some other concerns I would like.
So in this analysis, you assumed a more or less Newtonian fluid, right?
Yes.
What would happen if
you take a non-Newtonian one. So if you take something like what if you take a non-Newtonian fluid? How would the phenomenon change?
All right. So you want to answer?
So, I mean, non-Newtonian fluid can mean a lot of things. For honey, what we usually think about is that it has crystals in it. So you're not really thinking of a non-Newtonian fluid in the sense that it's a fluid. You're thinking it's a colloid because there's particles in it. At that point, if you look at the extreme case, it starts breaking up more since you start approaching a solid since you start having tearing more than just pinching because of surface tension.
Okay, then I think we can also give the mic to your team.
I have a question about some literature, and I do think you cited it, so you're probably familiar with it. The paper is called Dripping Honey Explained. It's from 2013 in APS.
Yeah.
And so basically they also use the silicon oil to explain the honey phenomenon. And in their model, they find that also for many cases, the viscosity does not matter so much, but their breakup or their theoretical model overestimates the breakup length. So I was wondering, did you, if you're familiar with the work, take an approach at solving this overestimation? And if so, then what is your contribution?
All right. So about the breakup length, yeah, I mean.
So if you look at the formula we gave, it's for a constant jet, and you need to remember that our jet stops and goes back up. So the hypothesis they use in that article is that it doesn't go back up. So we can't use the same formula. The formula can give us an idea of the importance of each parameter, but it's not directly applicable to our problem.
Do you have remarks?
No, I don't have remarks on this one. Actually, I just wanted to mention that since we were just talking about like all of these formulas, maybe it's a good idea just to go on and think about like how other parameters are, how we can describe the system more intuitively, go back on the intuitive way. And maybe I just dropped the word Reynolds number here. Reynolds number is kind of like a measurement of, or a number that measures the influence of inertia in relation to or over the stickiness or the viscosity. Maybe you have, to the opponent, you have thought about this, and do you think how does the Reynolds number influence like the different your different free regimes of motion?
So yes, so this is interesting. Actually, if you change the Reynolds number, I mean, if you had a jet in your regime, you don't have any more oscillations. So it is not really relevant to speak about the rising time since there's no rising time basically. So it is relevant, I think, to calculate this Reynolds number in the regime of the oscillations, which we did. Okay. So that would be my answer.
Okay.
Okay. Do you have a last point to make about this? Or?
Yeah, I think like Reynolds number, as I said, relates inertia to the viscosity, and viscosity like inertia drives the motion. Viscosity kind of damps and stabilizes the motion. So
Thank you. The time is up, and now the reporter has 1.5 minutes to give concluding remarks.
All right, so I thanks a lot the opponent and the moderator for the interesting question about clarifying also many things about this flow rate that we decided to vary by this syringe pump that we used. So just to go back a little bit on the work that was done and the improvement of everyone here. So we're able to see that actually the time of the oscillations themselves does not depend on the surface tension. Does not depend on the viscosity, sorry, but does depend on the surface tension and the flow rate. So we studied all these different flow rates to see actually on a spoon when the flow rates vary, what does it change in terms of the period of the oscillation, and it's what you have here on the top. Then we were also able to study these different regimes when you have oscillations. And you brought up an important thing, which is that we clearly had to state that in this problem, we are speaking about the oscillations, and that in this oscillation problem, you have these three different times that you can study, which is not anymore the case when you have jets. And we clearly defined the limits between jetting, transition, and oscillation regime, which is the thing we study here. However, the viscosity is actually of importance when considering the breakup length, but not the period of the oscillations. So thank you for all the discussion, and yeah, I enjoy it.
So thank you for this very nice discussion. I invite all speakers to the stage, and now the jury has time to ask questions. Please, again, be very short.
Okay. Hello. Okay. So hi, thank you for the presentation. Can you go back to slide 32, please?
Yes.
It's not this one, sorry. It's the one that you calculate the Reynolds number.
Yes, it should be the rising time, so it
Yeah,
should be this one.
Here,
Yes.
okay. So, what is H in your formula?
All right. H is what we do have here. So it's the length, the characteristic length under which the velocity is changing. Because you know that if you want to calculate the velocity, it is the dynamic viscosity times the Laplacian of the velocity. And so what we want to do is to know which is the characteristic length of the variation of our speed. And so we said that it was constant at the tip. And so what we could do, but it's not what we have to do, is to consider that this would be the characteristic length, but it is not. It is actually that, because here it's not moving, and here it's moving at a constant speed, so the variation are due to this characteristic length.
Okay, and what about the density? Because you use like some fluids that had like smaller density than honey, right? I think it was 1.5 for honey,
Yes.
and then
Yes.
and density is there, right, to calculate your Reynolds number. So
Yes,
how
actually.
does it influence?
Yes, what we did is that, actually, if we look at that, yes, here you have different density, but it is, I mean, the ratio is very small if you compare with the different ratio we could have between the different viscosity. So, I mean, it is roughly of the order of magnitude of 1 if you make the ratio, so it doesn't change the order of magnitude that we calculated.
Okay.
Okay.
Okay, actually, my question was covered. Can I move on or just start?
It's okay. Yeah.
Okay, I'll come back.
Well, the discussion has circled around whether this is representative of an actual spoon or not, and if the model is applicable to the real-life situation. I would like, with just a sentence, first the opponent, then the moderator, and finally the reporter, to describe if the model that you were just discussing is representative of not of real life.
First, me? Or, okay. So I think like when dropping from a spoon, there are very different effects. For example, like the nozzle is symmetric. The spoon is not. There are very geometric influences, and there's like friction when you have on the nozzle. There's this shear stress you have when you drop out of a nozzle, and also the motion, the flow rate is very not constant when you drip from a spoon, because the mass just becomes less when you have honey from a spoon, dropping from a spoon.
Yes, so I particularly agree with the last point. If you have honey flowing down a spoon, then first of all, the mass flow rate is not constant, and the mass flow rate significantly depends on dynamic viscosity, which will then also be why the period of dropping is not constant in time and also depends a lot on viscosity. So I think this was a source of confusion.
Okay, I do completely agree. However, what I would say is that if we want to study the spoon, we have to have the control on the flow rate to see, because it varies on the spoon, how the fact that it varies affect our oscillations. And I mean, at the end, we have all the answers of what would happen of the spoon, because we know what happens for each of our flow rates, because we derivate like all the flow rates possible, we try different viscosity, and so we should be able to predict thanks to that, which is what we did. So we should be able to predict thanks to that what happens on the spoon. Yeah, that's my answer.
For the opponent first, in the reporter's rising time, they elected to neglect gravity. Do you think that's a valid assumption?
No. Also, I think I mentioned it in the discussion at one point. I really do not think that gravity can be neglected, because I think it's a driving force here, and also only because of the mass flow also coming from the top, even though the drop is rising. I think it's really not something we can neglect here. So.
Yes, could I answer also? Okay, so what's here, you have that the surface tension, let's call it this, is equal to gravity. And so it means that if you take this volume, these two forces are equal. Then if the drop is falling and that is just cut here, you don't have the mass, you still have the surface tension because the radius here, that's not vary that much between this and this. So I think personally that the surface tension is now very high compared to the gravity.
I have a question. Could you please pull up the slide, either conclusions or the slide where you had this log plot of period versus mass flow? If it was just there.
Yes.
For example, this one. I think on the next slide it was bigger, but it's fine. So I see this very interesting. You see, it's below the line, then it's above the line, then it's below the line, then it's above the line. So that's your measurement. That's a question to you, and then to the opponent, let's say. Do you think that's a statistical deviation, or there is some interesting physics here in the fact that it seems to oscillate around the slide?
Okay. Would like my just my.
So maybe the way to see it is that, I mean, in terms of equilibrium, when you're at the equilibrium between surface tension and mass, you're going to start falling. The thing is, the very beginning of the fall, before we have a large drop for the first few millimeters, we're going to be slowed down a lot by viscosity, which means that our pump is pumping more fluid into a drop that already has enough mass to fall, and so that mass is not going to the next drop, which means that there is a second order term at a fixed flow rate on periodicity that is linked to viscosity.
Okay, does the opponent agree?
Yeah, this might be an effect, but actually I think since there also are no error bars included, it might also just be like a statistical influence. So, yeah.
Moderator?
They are error bars. You can see them. It's just very small.
Oh, okay.
So the effect is more significant than the error bars.
Okay, we should continue.
Okay, very quick and answer just with a number. Let's say you take your setup and you have through that a constant flow rate on a spoon, and then you analyze what happens of this like dripping and stuff. How well, again, just with a number, between 1 and 5, would you say you can predict what happens to this dripping depending on the spoon depth, width, and shape with your model and your results?
I'd say 4.
Okay, thank you. Moderator?
Can you clarify? I have a constant mass flow rate on top of a spoon, and then it flows down the spoon.
Yeah, yeah.
Oof.
So like we remove the problem of the constant flow rate.
Okay. Well, in that case, some 2.5 maybe.
Okay. Diplomatic.
Yeah, I would agree with
Okay.
the moderator.
Thank you.
I think it was slide 11 with this table of glycerol honey parameters.
Sorry.
11 is other side. Yes. So in your experiments, which out of this liquid did you use?
To compare the effect of surface tension, we use glycerol and silicone oil at the same viscosity because you can choose the.
Okay.
Okay, and I have a question about those parameters, because all of them depends on the temperature, especially for the honey, which is in the room conditions a super cooled fluid, because the melting temperature is above room temperature. So how you expect to change this period with the increase of the temperature? And this is a question for all of you. How those effects combine, because both surface tension depends on the temperature in some way and viscosity in some other way.
All right. When you are increasing temperature, you are lowering surface tension and viscosity. That's the experiment she was talking about. And that's why when you just hit your honey, you can see that it will go into droplets far more like before, because the surface tension lowers and the viscosity lowers. So as we know, dependence on viscosity and surface tension, we just have to see how these parameters depend on the temperature for your honey, and then we'll be able to predict the behavior.
May I comment? Yeah, okay, so I agree with you that the frequency will be increased like this. And I want to add that also, because we're talking about a spoon, right? The shearing force due to the viscosity being lower actually leads to a higher flow rate, which also then leads to a higher frequency even.
Yes, I agree with both of you. The frequency will significantly increase.
Okay, thank you. And I just ask 2 more jurors who didn't ask questions to ask questions. So can you please pass them the mic? No, you should ask questions because. Okay, then thank you everyone for this nice fight. Okay, so quickly. So lunch is until 4, but please proceed straight there. Go eat. Except the jury, you have to give grades first.
And the announcement ceremony will be at 4:30 in this auditorium.